Okay, great. I guess let's go. Well, welcome again. Thank you all for being on time. I'm sure we'll get some stragglers in. We'll just do our best to accommodate those folks coming in. But thank you for being here, and thank you for being on time. So yeah, like we were saying a moment ago, right? We're here to talk about telescopes so that if you buy one, you're not just going to end up putting it in the closet, and find it again a decade later. And as you saw a moment ago, because I clicked ahead by accident, right? My alternative title for this is kind of light funnels and time machines, right? Somewhat a more poetic way to look at it. Because that's what these things really are, right? And we'll touch on that briefly, but mostly we'll talk about just the equipment aspect today. So there's a lot to talk about. Here's kind of the high-level outline, right? So this is in 3 parts. The good news is between the parts, there's a cookie break each time. Okay. First part, we'll spend some time setting expectations and talk about why are we using telescopes at all, right? Just to make sure we're clear, why this piece of equipment. A little bit about image formation. Then we go back to setting expectations a little bit, and then we'll just talk about telescope as a system. How do we think of a telescope as a collection of pieces, so that then we can talk about those individual pieces more in the subsequent portions, right? So we'll try to break it down and describe each of these things. And then at the end, we'll kind of cover some telescope alternatives, right? Because telescopes, they're all just tools, right? And they're different tools for different use cases. And so maybe sometimes you actually don't want a telescope, right? Maybe sometimes a slightly different tool is better. In binoculars, you'll see we'll have some binoculars on the floor, right? So that's one of those alternative tools. And then we'll wrap it up with just kind of some accessories and just miscellaneous things that might come up. So we've got like a 3-hour thing scheduled for today because there's just so much to talk about. In fact, there's even more than we can fit into those 3 hours. So I'm going to skip some stuff, as we go through today. And the intent is that later we'll send you a link to a short video, or I don't know how short it'll be, probably another 40 minutes or so. If you want to look at the stuff that we skipped, you can do that on your own after, right? And it'll fit in the context of the bigger conversation we've had here today. So I hope that makes sense. As we go through, feel free to ask questions. I mean, that's cool, right? And of course, we'll have the breaks, the cookie breaks, where you can look at the equipment. You can ask us questions about that, right? And ultimately, we're here for you, right? So you can help us, guide our progress here, right? If you filled out that pre-survey, by the way, thank you. We did look at that. And the long story short, it seems like what we've got planned should, meet everybody's expectations, I hope. But again, at the end, you can tell us how we did, and maybe we can learn for next time, too. Yeah. So, okay. All right, so so here we'll kind of jump into the first part here, where we're going to do some expectation setting, what you will not get from this presentation, right, to make sure you're not here for the wrong reason. And then, what you will get, the parts of a telescope, and we'll touch on telescope alternatives just really briefly at the very beginning, right, and then circle back to it one more time at the end. Then, like I said, why telescopes, and then some stuff about how images form, because that's a foundation for, what comes after. So what you will not get from this presentation, just want to be really upfront, right? There is no single best telescope, right? It's a common question, what telescope should I buy? And the answer is, I don't know, right? It's kind of like, what car should I buy? I don't know, right? It depends on what you want to do. Do you want to go really fast? Do you want to hold a lot of stuff, right? You might want a race car or a truck. And even then, there's no single answer for what's the best truck, right? Right? Ultimately, you need to do some research and see what best fits your use case. So we cannot tell you what to buy, and anything that will sound like a recommendation is really only some opinion, right? So you'll obviously hear some stuff from us, but even among Carl, Swami, and me will be your presenters today. You might get different opinions on certain things. So take that for what it's worth. Okay. You'll see a bunch of examples of equipment in this presentation. They're meant to be just examples, right? We're trying not to show you junk, obviously, right? At the same time, it may not be what you want to buy. Do some research around that, right? They're meant to be just examples. Okay. So this presentation won't teach you everything there is. There's always more to know, even though we're going to spend about 3 hours on this stuff. And ultimately, you'll still have to choose a telescope for yourself. Okay. But what you will get from this presentation is, right, you'll learn about the parts of a telescope system, how the telescope works, different types of telescopes and ancillary equipment, right? What are the different flavors and variants? Other factors, that make for good or bad viewing, and I skipped over the trade-offs among different designs, right? That's often an important question, right? It's like, okay, you got this thing and this thing, there are trade-offs, right? This one is good at this one is good at this other thing, right? So it's good to understand those. There'll be some pointers for some additional resources, and ultimately the goal is to make sure you know more so you can talk better to others about telescopes, right? Maybe at star parties, right? Because if you talk to folks who've done this for a long time, they'll throw out all these different terms as like, what is all this stuff, right? You may not understand at first. And so I hope this will prepare you for that. Then ultimately you can choose your own equipment better and ideally avoid spending money on stuff you don't need. So to set the stage here, so major parts of a telescope are kind of four pieces, right? So I think of a telescope as a collection of four main pieces. The first one is what we call the optical tube. And that's often what people think of as a telescope, right? It's basically like this bit here, right? Optical tubes come in different shapes. We'll see what those are, but that's clearly one major part. And then the optical tube has to sit on something, right? It's not sitting on the ground. It's not hovering, right? There's something to hold it up. And that's in this case. This guy here, we call that the mount. And the mount breaks into two pieces. The mount head that allows the telescope to be kind of swiveled and pointed. And the whole thing then is sitting on some tripod or something to hold it up at the right height from the ground. Okay. And then the third really critical piece is what we call the eyepiece. And that's just a little doodad right here. Right? So often we think of this as the telescope, and again, that's kind of the main piece, the OTA. And that has a big lens in it or a big mirror. But the eyepiece here, has a much smaller lens assembly, but it's really half of the optical system. So it is also a really important part. And then the other fourth really important part is the finder, which in this case is in the circle here, or you can see different finders later. If you look at our sample equipment here, another really important part, because you have to know where you want to point your telescope. If you've never done this, right, you might say, oh, there's the moon up in the sky. Should be easy to find. It's right there. I can see it. But then pointing the scope at the moon is actually quite difficult. And so you need a tool to help you, and that's what the finder does. And if the finder is crappy, your scope won't work well. And that was actually kind of the failure of that very first telescope I had in a way, right, way many years ago. And yeah, and then this picture has like this little thing that looks like a beaver's tail. It's like an optional phone holder in this picture. You don't need that necessarily, but it happens to be in my sample picture here. Just to be clear up front, right? So binoculars can be an excellent alternative to telescopes, right? They are, great tools for looking in the night sky. They can be much less expensive than telescopes. They're much more portable. They may be easier to use. They have large fields of view. You can see much more of the sky at once, which can be a benefit depending on what you're after. And a downside, of course, is that you cannot see faint objects or resolve small ones. That's where telescopes come into play, right? But binoculars are great tools, right? And if you have one, dig it out. Try it for astronomy. It might be great. And then also, and we'll circle back to this at the end a little bit more, right? But smart telescopes have come onto the market over the last few years. There's a lot of them. We've got one sitting on the table there you can look at later if you want. And these are things that integrate telescope, optics, digital cameras, and small computers, right, into these different devices here that can automatically find and track objects for you. You control them from your phone or tablet, and that's where you see the image as well. And they work pretty well in light-polluted areas, like in San Jose City. But a downside is they don't give you a first-person eyepiece view, right? You're looking at your screen while the beautiful sky is above you, right? Which might be a it's a plus in some ways, but it's in my mind also a negative, right? So. So I see them as, not replacing, but complementing traditional visual telescopes. Okay, so we're here primarily for visual telescopes. So I want to be clear that we're not going to focus on astrophotography in this session, right? Some folks really want to take pictures of the night sky. Great thing to be doing if you want, right? This is not a focus for today. However, a lot of the stuff we talk about also lays a good foundation for astrophotography, right? But I want to be clear, if you're here specifically for astrophotography, this is not the focus of today. SJ does have separate sessions that talk specifically about that topic, though. We're not going to go into great details on binoculars and smart telescopes, but we'll visit them a little bit at the end. And ultimately, if you want to choose a telescope, best thing is to get in-person experience. And so I'll plug one of SJA's programs, right? It's called Quick Start. You can check out a telescope kit, basically, right? With a little bit of training, you get a telescope kit, something similar to that black thing sitting over there, with some accessories. You can borrow that for a period of time, use it on your own or at our star parties, and that can be a great way to learn without having to invest a lot of money, right? And then you can decide better what you might want to buy for yourself. And different astronomy clubs will offer stuff like this, perhaps, right? So you can check in your local area if this is not that area. Okay. There's a little bit of math ahead, so don't get scared. Don't worry, it'll be fine, right? But one key thing is that telescope equipment unfortunately uses both metric units and SAE or imperial units. It's just the way it is. Sometimes it's inches, sometimes it's millimeters. And so the magic number to remember, right, is 25.4 millimeters are 1 inch. And so yeah, it's just something to put into your brain when you look at telescope equipment and try to make trade-offs. There's a lot of stuff ahead, right? We're going to talk about a lot of new terms. Don't worry about remembering this all verbatim. That's fine, right? But even if you don't remember everything, later if someone talks to you, you might go, oh wait, this sounds familiar, right? And then you may know where to look and how to pick up that thread. Focus on getting a conceptual understanding, and you'll be armed with information so that the future will make more sense, right? Discussing telescopes with other folks. And maybe reading product descriptions, right? That's often something that's difficult. If you're trying to buy, you read all this stuff, it's like, I don't even know what they're talking about, right? With all their spec bullets. But after this today, I hope you will know a little better. So, okay, so let's see. Let's talk briefly about, why telescopes at all. So here's a nice view of the night sky. This is the winter sky. Some of you may recognize Orion in here. Orion is disappearing for this year, but it'll be around again, in the winter, next winter. And this looks nice. This looks pretty, right? But we like to use telescopes to be able to reveal some of the details that are hiding up there, right? And see, for example, the Orion Nebula up close, right? It's one of the jewels of the winter sky, and it's kind of an awe-inspiring object if you have not seen it. So that's kind of why we want to use telescopes, right? And so when we ask the question, what functions does a telescope perform? A common answer is it magnifies stuff. And that's true, it does. But magnification is actually not the most important function, right? A more important function is really to collect light, to make faint objects appear brighter, okay? And to put that in context, right, our eyeballs are collecting light right now. And we all have our little pupils, right? The little black dot in the middle of our eyes, that's how the light's getting in. And then our retina senses that, and our brains do a bunch of processing, and we see stuff. And how big is this hole that we have here, right? So it's 2 millimeters in really bright light, maybe 8 millimeters in dark light, or rather, I'm sorry, in darkness, right, at night. And it varies with person and age. It's harder to open that pupil up as we get older. But either way, it's small, right? And so really what we want is a light funnel, right? Something that can collect more light and kind of squeeze it down into our eyeballs, if that makes sense. Okay. And so binoculars and telescopes actually are light funnels, right? So that's really how to think of these devices. And so what's happening here is, right, so we have these binoculars and they have these openings here that collects light. This is, in this example, this is about 50 millimeters or 2 inches. And so it's collecting light with this area and then squeezing it down such that it shoots out over there and pew, right, can enter our pupil, right? It's as if we're making our pupil that much bigger. Does that make sense? Okay. And so in this case, right, with this arrangement, we get to collect about 39 times as much light, right, from that larger aperture opening of the binoculars. This telescope here is a 100 millimeter or 4-inch aperture. And so with that, we're collecting about 156 times as much light. It's a lot, right? So again, it's as if our pupil had gotten from this size to about this big. Yeah. And so how does this light funnel work, right? So we can imagine, maybe there's some stars over here, and there are light rays coming from some distant object, out in space. And that light is now shining into an eyeball, right? Not all of the rays will enter into our pupil, right? Like we just said, the pupil is small. So a lot of the light rays that are coming from whatever's over there are going to miss our pupil, right? And they're lost to us. But okay, what if we put a lens here, right? If we put a lens in this path. So now the light rays are hitting this lens, and this lens will bend, or we say refract, that light. And we get behavior that looks like this. So all those light rays are now going pew, right? And they're going to converge at a point here that's called the focal point. There's a distance here called the focal distance, right? So that's the distance from the lens to the point where everything converges. And yeah, so now if we put our eyeball there, what do we get? Well, the bad news is it's not working yet, right? We haven't completed our light funnel because the light rays that are going to our eye, they really don't line up like the original ones did, right? These were all parallel as in my drawing, right? But over here, it's now this conical thing. So this is not working yet as a light funnel. But we can add a second lens to get, yes, sir? Too much glare? Okay, sure. Is that okay with you guys? I guess, yeah, okay. Okay, I'll keep going though. Is that good? Okay, thanks. So then with the second lens, so if we put a lens, oh yeah, much better. I can see it too, actually. So with the second lens here, right, so now we're taking the light rays and we're again arranging them so that they're parallel, kind of like they were before. But notice that they're much more densely packed, right? So we've basically squeezed them down. So yeah, so we had all these light rays, a lot of which were missing our eye before, and now they got squeezed down so that they can all enter the pupil, right? And ta-da, that's our light funnel. Does that make sense? Basic concept, right, for how our telescopes work. And binoculars do the same basic thing. So, if we put some names to these things, this is what we call the objective lens, or, specifically in the context of telescopes, this is the lens that's sitting in the telescope tube, right? So that, you can't see it right now, but that lens is basically sitting here. And if you want, you can look inside later and you can see it. And then that second lens over here, right, that's the eyepiece lens, right? That's the one that's actually sitting here in this assembly. Okay. And then we speak of the diameter of the big lens here, and that's the aperture, right? The size of the opening that's collecting light for us, right? The opening of the funnel on its wide end. And so the larger the aperture, right, the more light gets collected and funneled, right? And the more light you can funnel, the brighter the image ends up being. Because yeah, so here, earlier we just had these light rays, but if I expand the aperture a little bit, right, I can pick up more light rays here, right, and then they can also get funneled down. Does that make sense? Everybody with me? Again, please interrupt if this doesn't make sense. Please ask, right, because we'll make sure that everything downstream will make sense. And so, yeah, so here's a cartoon of this telescope, right? This right here is where the light gets collected. That maps to this thing here. But of course, here this is drawn flat because we've drawn just a ray diagram on the screen. But in reality, this is, of course, a three-dimensional thing, right? And the lens is round. So we measure aperture and diameter, but really what matters is the aperture area, right? Because it's the area that's collecting that light. Are you okay over there? Yep, okay. So if you're buying a telescope, right, they're going to tell you this number, right? But really what matters is this area here. So let's think about diameter versus area for a moment, right? If you remember your math, remember I told you there's going to be a little bit of math ahead, right? So area of a circle is pi r squared. And essentially r is the radius, so the diameter is essentially twice the radius, right? So you can kind of write the whole thing as area is pi times the diameter over 2 squared. Okay, that may ring a bell from math some time ago. Right? And then so if we put that into an example, so let's see here. So here's a diameter of 4 units, could be 4 inches. And here's an aperture diameter of 5 units, right, or 5 inches. So the area for this is 12.6, say, inches squared. And down here would be 19.6 inches squared. Right? So that means while the diameter scale, right, 4 to 5, went up by a factor of 1.25, the area actually went up by a factor of 1.56, right, from 12.6 to 19.6. Does that make sense? Right? So the key takeaway here is, we speak of telescopes in diameter, aperture, but really what matters is the area, right? And it's sometimes not obvious how they map. So it's important to maybe do that mental math a little bit. And so here's an example, right? So we've got actually telescopes like this on the floor if you want to look at them, right? This is a 6-inch version, and this is an 8-inch version. Otherwise, it's all the same thing. And so up here is a lot of numbers, I know, right? But we're going to just kind of pick out what we care about. So if we're scaling up the aperture diameter, we're going to scale it from 6 to 8. So that puts us here, right? So the aperture diameter is increasing by a factor of 1.33. It doesn't sound like that much, actually, right? 6 to 8 inches, it doesn't sound like that much. But the area is actually going to scale, oops, wrong button. The area will actually scale by 1.78 from a 6-inch to an 8-inch. And so it's almost 2x, right? It's getting close to twice as much light, even though we only added a couple inches of aperture to the diameter. Does that make sense? Yeah? So important to keep that kind of stuff in mind. Same idea here. We're going from a 102 millimeter to a 127 or 4 to 5 inches. So the diameter scalar is 1.25, but the area scalar is actually 1.5x, a little more. So if you want to brag about your telescope, right, we don't usually brag about magnification, right? But what we brag about is the aperture, right? Size matters. The bigger that light funnel, the more light you collect, the more you can see faint objects. So there's kind of an important conclusion here then, right? So don't buy a telescope that attempts to sell you magnification. Like this thing, the box brags about 525 power. It sounds really impressive, but it's not a useful number, actually. You'd never use it. This would not deliver for you, okay? So if you see telescopes that brag that way, it's almost certainly not something you'd want to buy, okay? And so these are all things I saw in a local store, actually, right? They're all actually relatively inexpensive, but same kind of thing, So I recommend that, just back away, instead, after you're done here today, you'll probably have better tools, right, to choose a good telescope for yourself. And I call this light funnels and time machines, right? So we talked about the light funnel part, right? But time machine, just to put this into context, right? Light travels at about 300,000 kilometers per second. So when we look at a distant object, we see how it appeared in the past, because it took time for that light to get here, right? The Whirlpool galaxy, for example, one of my favorites, is 23.5 million light years away, right? So when we look at it through a telescope, and actually literally just did it on Friday, I looked at this through somebody's 22-inch telescope. And so we saw it the way it appeared 23.5 million years ago, because it took that long for the light that we see now to get here. And like the James Webb Space Telescope, right, it can look almost to the beginning of the universe, essentially, right, back in time, which is pretty mind-blowing. And so yeah, telescopes are time machines. Isn't that cool, right? You're surrounded by time machines, in this hall. Just a little bit on image formation. So kind of give you the punchlines first, and then we'll talk about it a little bit more. And this is one of those areas where I'll skip some content. And if you want to get that next level of detail, you can look for that video I mentioned earlier, right? So we'll give you a follow-up after this session. So the position of the lenses determine whether an image is in focus, right? We talked about the objective and ocular lens. How they're positioned is important, so you get a focus. The focused image may not be right side up. And focal lengths of the lenses determine the magnification of the image. Okay, so let's touch on these a little bit more now. And then, like I said, there'll be even more detail if you want to follow up with the video. So to focus a telescope, the distance between the objective and eyepiece lenses needs to be adjusted, right? So this is the same picture we had before. And the first order, right, that there has to be right distance here between the lenses such that these focal points sit on top of each other, basically. There's some other factors that come into play, but the first order, that's kind of it. And so telescopes have a knob to do this, right? So here in this picture, there's a little knob there, and actually we can do it right on this one. This has it as well. So, and notice if I turn this knob, right, it physically moves this in and out, right? That's physically adjusting that lens-to-lens distance until you achieve focus. So we're physically elongating or shortening the scope and the lens-to-lens distance. Okay. And then, oops, sorry. I almost went into the details, which we'll actually save for later. Otherwise, we're going to spend too much time. Image formation. So this is kind of the upside down part, or rather the right side up, upside down thing. So an astronomical telescope will form an inverted image. Okay, so that's an important thing to be aware of. So here's the Golden Gate Bridge, of course, right side up, the way we see it with our eyes. If you were to look at that through an astronomical telescope, it would look like this probably. So it's actually flipped over, right? It's inverted. Now telescopes for terrestrial use, they have extra elements to kind of flip things back so it's correct. Like if you do birding, some people like to do bird watching, for example, or whatever, right? If you look at things on the ground, you want them to be a right side up the way you expect, But for astronomy, we want to minimize the number of optical elements, because every time we add another thing into the light path, we lose a little bit of light, or light gets scattered, and the scope then does not perform as well. So we say, fine, we don't care about the upside down. There is no upside down in space anyway. In sci-fi movies, it's always cool. All the starships always meet, facing the same way. Just once I want to see them come, like all upside down, right? Because that's what would actually happen. There is no agreed upon up in space. So, because we don't have it up-down anyway, we don't care that things may be flipped or inverted, right, in our astronomical telescopes. So magnification here, like I said, is a function of the focal lengths of the telescope and the eyepiece. And we speak of magnification also as the power of the device, right? So like binoculars that are, let's say, 10 power, right? That means they have 10 times magnification or whatever, okay? And we can calculate that magnification by taking the focal length of the ocular lens, the objective lens, this guy, right? And then the focal length of the ocular lens, and we can just do a division. It's actually pretty simple. So here's an example of this, right? And again, we have telescopes and stuff like this on the floor if you physically want to see what these look like. But so here's a telescope that has a 2032 millimeter focal length, about 2 meters, okay, of focal length. And then here are 2 eyepieces, ocular lenses, right? 32 millimeter focal length or 12 millimeter focal length. So we said, okay, we can calculate the magnification by doing this division. So that's what this table is doing, right? So here is the next star A to C, this guy, about 2,000 millimeters focal length for the main telescope, and then 32 or 12 millimeters for the eyepieces. And so with this combination, we get 64 times magnification, just doing this division. And here we get 169, or almost 170. Is that making sense? Okay. And now if we had a different telescope to start with, right, if we didn't have this one but this one, same eyepieces, right? Now the telescope has a smaller focal length, 714 millimeters, and we do the same divisions, right, and we get magnifications of 22 and 60. So what you get is a combination of the telescope you have and the eyepieces you have. Does that make sense? Okay. And later we'll talk more about what magnification you might want, right, for particular objects. But so that's ultimately how you might choose eyepieces, right? What magnifications do I want given the telescope I have, right? And that might choose you to drive you to buy a, 12 millimeter eyepiece or something. Hello. Okay, the last thing I'll bring up here, I think, is a thing called focal ratio. And I'll tell you right now, this is one that confuses me, or confused me when I was first getting into this. If you've done photography, you'll have a concept of this. Okay, but let's kind of look at it together. So yeah, so telescopes have a property called the focal ratio. It's also called f ratio, f stop, or f number. And it's written as f over n, where n is some number, like 7 or 5 or whatever. Okay, and it's basically defined as the focal length of the ocular lens. Sorry, I keep saying it backwards. Of the telescope lens, right, the objective lens. So this focal length here, divided by the aperture. And so here's an example of this, right? So focal length of the telescope or the objective lens is 700 millimeters, let's say. Let's say the aperture is 100 millimeters here, right? If I do that division, I get 7, right? 700 over 100. So this would be an f7 telescope. That's nice. Okay, now, and again, we're going to skip over some details here that you can get a lot more nuts and bolts on this in the follow-up video. But one key thing to understand, or at least remember, is that there's a notion of a fast telescope, and that's the confusing part in my opinion. Again, cameras, you've heard this before, right? But people speak of a fast telescope, and in photography what that means is that essentially a faster lens, people speak of fast lenses like fast telescopes, and what they mean is that, you can basically take a picture with a faster shutter speed. Does that make sense, right? Even with your iPhones, if you take a picture at night, it takes longer, right? Because the phone will go click, click, right? It's actually simulating the shutter sound, right? The shutters are actually electronic. There's nothing mechanically opening usually. But that's what cameras do, right? They kind of start looking, they collect light for a while, and then they're done looking, right? And depending on how bright it is, they may collect light just for a fraction of a second or for multiple seconds. And with a faster lens, you can get away with collecting light for a shorter time. That's the basic idea. Okay, but for telescopes, this can be confusing, right? For visual observing, it's not even that meaningful, so I would say don't even worry about it. Okay, so if you're not doing astrophotography, you'll hear this term, fast telescope, but you know what? Screw it, don't sweat it too much. Okay, but for photography, this does matter. And so here's a couple examples, I guess, right? So if we assume that we have a 500 millimeter telescope focal length, and the aperture is 50 millimeters, right, then that would be an f over 10, right, because we're just dividing the 500 by 50. If we have a larger diameter aperture, right, so but the same focal length, now it's becoming an f5. And this kind of makes sense. This intuitively makes sense to me, right? Because we just said earlier, if you make the aperture bigger and nothing else changes, right, you're just collecting more light, right? We've made our light funnel bigger. So that is kind of a faster telescope because it just collects more light, right? If you put a camera there, you can take an image faster, right? Because you're just collecting more light because you've just made the aperture bigger. You kind of with me on this one? Okay. The second one is the one that confuses me more easily. Right? So here, now we're saying the aperture is fixed, right? So let's say the telescope is 150 millimeters. That's it. But what we're changing is the focal length. Here's the focal length, 900 millimeters. And this one uses different lenses, same size, right? But the focal length is different. So here, my focal length, my focal ratio becomes f/6. And here it will be f/4. So this one, the claim is it's the faster telescope. But why, right? We didn't actually change the opening, right? We're collecting just as much light as we did before. Does that make sense? Right? So this is where, to me, it was like, I'm not sure I get this. Okay? And I'll just give you the answer. If you want to hear a little more, you can follow up on the video. Okay? But the short answer is that, the telescope lens, the main lens here, forms an image here that's called the prime focus image. That's the image you project onto a camera sensor if you want to take a picture there, okay? And with this arrangement, it turns out that prime focus image becomes more concentrated, right? So actually, it's focusing the light onto a smaller area, so in a way that the sensor sees, each little pixel sensor sees a little more light. Okay, and I'll leave it there for today, right? So, but it's just to give you a taste. If you care about this further, right, we'll give you some follow-up material. Okay. Okay, the final thing I want to point out maybe here is, so photographers will also know about this concept of depth of field. Yep, I see some heads nodding, right? So you may know from photography, right? Depending on how you set up your aperture, right, and what lens you have, you may get a picture where your foreground image and the background image, they're all relatively in focus. I mean, this is your focus part, but the branches, you can see them, right? You can see there's other stuff behind it. It's somewhat clear. Whereas here, right, the background is very blurry. Only this is in focus, right? So that's the concept of depth of focus. Telescopes kind of have a related concept of depth of field, excuse me, and then telescopes have a related concept of depth of focus. You can think of it as the same basic thing, if you will. And so what that means, though, is to kind of get to the punchline here, right? So if you have a telescope with a higher F number, okay, they tend to be more forgiving of lower quality eyepieces. Right, so this may affect your purchasing decisions, right? And again, I know we're skipping over some details here for time, right? But feel free to ask, or again, I'll refer you to the video we'll give you. If you have a low F number telescope, right, you may have to spend more money on eyepieces such that the telescope really works well, right? So if you buy like a fancy F5 fast telescope, you may also have to buy fancier eyepieces. If you have an F10 telescope, you can get away with less expensive eyepieces. That's kind of the key takeaway. Okay, so just to quickly review this, so a telescope produces an inverted image, right? Maybe flipped over. For the eye to see a clear image, right, the image needs to be in focus, and we do that by physically changing the distance between the lenses. Okay. So every telescope has some focusing mechanism for this. And then magnification is the ratio of the focal lengths, objective lens divided by the ocular lens, or telescope divided by eyepiece, right? So these are kind of synonyms in our nomenclature today. If you have an eyepiece with a smaller focal length, that basically gives you higher magnification. And a greater focal length eyepiece or ocular gives you lower magnification. That's the general trend to keep in mind. So as your focal length of the eyepiece gets bigger, your magnification goes down. And then finally, we talked about this focal ratio thing, right? Which we said, yes, that can be confusing. The focal number is this thing called n. It's the telescope's focal distance divided by the aperture diameter. Lower n numbers give you faster scopes, again, which may be a little confusing. If you want to learn more, we can tell you more. Okay, and then here's a really dizzying picture. The point is there's a lot more stuff you can learn about this if you want to go for it. In the follow-up video, we'll do some more ray diagrams if you're really interested in what's happening kind of under the hood, if you will, right? And then there's a lot more to learn out on the web if you want. right? But obviously these things are way too busy for us to talk about in detail here today. And even the cookie sugar may not keep you awake through this, so we'll skip this. And with that, let's see, we're going off into segment 2. We'll talk about some more expectation setting. What views do you expect from your telescope, right? What should you expect to see? Sometimes people buy telescopes, then they're disappointed. I thought it would be more, right? I don't know, or something, right? So we want to make sure you know what to look for. We'll talk about some characteristics of the view that are important to understand and talk about, and then telescope as a system. And since you're probably tired of listening to me talk, Swami, do you want to do the expectation settings part 2?
All right. Okay. So this was a really good introduction to what we are talking about here. But let's talk a little bit more about what to expect and what not to expect, right? I'm sure everyone has seen an image, either this image or an image like this, right? This is the Andromeda galaxy, and it looks beautiful, right? Lots of detail, lots of color. The question is, will you be able to see an image like this when you're looking through a telescope, right? And I see some of you shaking your heads. So yeah, absolutely. You should not expect to see something like this when you're looking through a regular telescope, right? This type of image, it usually comes from research grade, large telescopes, and they're doing some good imaging, right? You can even get an image like this through these telescopes, but not when you're visually looking through those telescopes. But if you do imaging, use these telescopes to do imaging, and you collect a lot more light over a long period of time, you will be able to get an image like this. However, if you're just using a telescope to observe, you're most likely going to see an image like this, right? It's going to be relatively faint, not as much detail, and no color. You'll almost never see any color in an image like this. So just what you said, with a telescope like this, you're not going to get this image. However, you might be able to get an image like this. Now, even here, you can see there's a lot more detail, right? There's a lot of detail here. But this is what you'll get on a really great day or night. What do we mean by great day? We'll talk about that in a little bit, right? But if the observing conditions are really good and your equipment is really good, then yes, you might get an image like this. On kind of a good but an average day, it'll be a little fainter. It'll look somewhat like this. And then if it's not a very good day, if there's a lot of clouds, like a lot of moisture in the air, and we'll get into details of that, then you might get a very, very faint image, right? So this is the kind of images that you can expect to see when you're doing visual observing and not astrophotography. But even then, looking through a telescope is a very, very rewarding experience because you're actually connecting to the actual object that you're looking, right? Versus just looking at an image. Here you're actually looking at the object. The photons that came from that object, they're actually hitting your eyes directly, right? So it's a pretty satisfying experience to be able to see the object, even though you're not seeing as much detail and as much color as you would like to see, but it's still a very satisfying experience. So we talked about a good viewing conditions or good day where you can observe a lot more detail. What does that really mean, right? So there are many different things that go into whether the viewing will be good or not, right? Of course, we talked a lot about the size of the telescope, the aperture, right? So the aperture and the quality of the telescope, and we'll get into the quality also later on in the presentation. Yes, those things definitely will make a difference. But in addition to that, right, where exactly is the object on the sky? Is it low on the horizon? It is somewhere a little bit up, or is it straight up? If it is very low on the horizon, you're looking through a lot more atmosphere. So it's not going to be as clear as when it is higher up in the sky, right? So that will not be a very good place to observe a faint object, especially. If it's straight up, yeah, you might get a pretty good view, but you'll probably hurt your neck, trying to look straight up. That's not the best place to observe an object either. So, somewhere in between, if it's somewhere in the middle, right, maybe about 30 to 60 degrees from the horizon, that's a pretty good place. If the object is there, then you'll probably get the best view. Also, where are you observing from, right? How high you are, right? If you're right on the ground in the middle of the city, there's going to be a lot of light pollution. Viewing conditions are not going to be that great. But if you go to a darker area, and especially if you're high up on top of a hill where you're above all the light pollution from the urban areas, then the observing conditions will be a lot better. Now, at SJ, we have observing sessions, public star parties we organize right here outside in the parking lot. And we also do in some dark sky locations, like Rancho, at Cañada del Oro, and sometimes we do at Pinnacle, sometimes at other places. The observing conditions here in this parking lot are not that great, obviously. We do turn off the parking lot lights, so we bring some darkness to this location, but we are in the middle of the city. So the observing conditions are not going to be that great. You can still see the brighter objects, but the faint objects, it's kind of hard to see from here. Then there is also the condition of the atmosphere itself, right? How much moisture is there in the air, right? That's going to make a difference, because if there's a lot of moisture, a lot of other particles in the air, that will degrade the quality of the images that you can see. Also, is it very windy? Is it very turbulent? And not just here on the surface, but high up. If the air is very turbulent, then the density of the air is changing constantly, and that means the rays that are coming through, they are kind of bending, not quite coming straight all the time. So you'll see a lot of shaking, a lot of turbulence in the image itself, right? So if it's very still, then you'll get a better quality image, right? And then finally, the temperature of the telescope itself, right? If your telescope, you've just taken it out of the case, it might be pretty warm and outside air is very cold. So again, the difference in the temperature, it'll cause some air currents, right, as it's trying to balance the temperature inside the telescope and outside the ambient temperature. So that's also going to affect the quality of the image. And lastly, the phase of the moon, right? If the moon is up there and it's very bright, that's going to wash out a lot of the fainter objects. So all of these things go into determining what quality of an image can you actually get. Right? Yeah. Yes.
On the position of the object, right? We actually do look straight up. It depends on what you're using as a tool to look, right? Binoculars, yeah, it's a neck breaker, right? If you're just doing this, you're probably going to tip over and fall backwards, right? Unless you're in a nice comfy chair. But telescopes actually have some devices, right, to help you or allow you to look straight up. And so depending on what you're looking through, right, straight up is actually where you want the object to be, for like the perfect possible view. And we'll talk about that a little bit more later. Right?
Yeah, especially something like this, right? You have a diagonal here, so your telescope may be pointing straight up, but your eyepiece is horizontal, so it's a little easier.
Yeah.
Good point. All right, so we talked about all these different conditions. Before we actually head out to an observing site, we can also check what the viewing conditions are going to be based on the forecast, right, the weather forecast. And we very frequently use a map like this to determine what the viewing conditions are going to be like. There's a URL there, cleardarksky.com. You can go there, put your location where you want to find out how the viewing conditions are at that location, and it will show you a chart like this, where it is showing you like a few different metrics here. And it's arranged by time, right? It's a 24-hour military time starting from 00 going all the way up to 24 for that particular day. And for every hour in the day, it's showing you how much cloud cover there is. Of course, if it's completely overcast, you're not going to be able to see anything. But you can see how much cloud cover are they expecting at that location at a given time. What's the transparency? Right? What is transparency? Transparency really means what an estimate of the amount of water vapor in the air, right? As we talked about, if there's a lot of moisture, that will affect your viewing conditions. So transparency talks about how good of clarity you can see in the air, you can expect in the air. If it's white, that's not going to be very transparent, but it should be a darker color. Seeing is the measure of air turbulence. I don't know how they came up with these terms that seeing means this and transparency means this, but that's what it means. Seeing simply talks about what's the measure of turbulence in the air. If it's very still, you'll have better viewing conditions. And then the wind, humidity, and temperature, etc. And of course, darkness, right? Darkness is simply, this is the daytime, which is all white, and then the nighttime. So what time of the night it's going to be the darkest. So you can kind of get an estimate from that also. So this will give you an idea of how the viewing conditions are going to be at a specific location that you're planning to go and observe. All right. So next section, characteristics of the view. Carl, I think you're going to talk about this.
Okay, so when we're looking at an object, we're considering a bunch of different characteristics. Obviously, Wolf talked about how aperture affects how much light we can see, or sometimes we call that how bright something is, or the contrast, the difference between the light and the dark areas. If there's a big difference between the light and the dark, that's a higher contrast, and that's something that's desirable in our view. How much of the field we can see, how zoomed in it is, what the colors look like, if they are more or less correct, or if there's some aberrations that are causing little rainbows or other distortions. Resolution, how much we can see, flatness of field, if things get kind of distorted towards the edge of the field, and then other things that can go wrong. So first off, the brightness. As you can see on the left, this dimmer object looks like less bright than the right object. I don't know how else to say it. It's pretty apparent, I think. If you can see it more easily, if it looks like there's more light there, then it's brighter. Larger telescopes with larger apertures make the view brighter. Pretty simple. Contrast is a little more interesting. One of the main factors that affects how much contrast you see is how much light pollution there is, or the quality of your optical elements. If there's a lot of light pollution, then basically there's street lights that are scattering little photons kind of all over the place, and then everyone's porch lights, and all of that kind of adds up into this glow in the sky. And all of that creates all this extra light that detracts from the object we're trying to see in space. And so it gets kind of washed out. And so you can kind of see that on the image on the left, how it's pretty bright, and you might even say that it's brighter than the one on the right. But the stuff that's brightest is, aside from the middle, the bright stuff around the edges is all background. And that's all scattered light from somewhere else, either light pollution or something in the optics that is creating a reflection that you don't want. Whereas on the right-hand side, you have more contrast. The darkness, the dark area that's supposed to be dark is really dark. It's like pitch black on this slide. And the bright core that represents the actual object we're trying to see is really bright. So that's really good optics and or really good dark sky without pollution. Next up is the field of view. So we talked about magnification, which means you can zoom in or zoom out of something. But in this case, the magnification is identical between both images on the left and the right, but you can see more of the Golden Gate Bridge on the image on the right. And that's what we call field of view when it comes to telescopes. You can have a smaller field of view, and that has nothing to do with magnification. It's just how much of an object you can see. And you can see, if you have a larger field of view, you can see more. You can see the area around it. In contrast to magnification, you could have the same field of view. So these two circles represent the same field of view, but one is more magnified than the other. And you can see that clearly in this image, where on the left-hand side, you can see the tall part of the Golden Gate Bridge, and on the right-hand side, you can see a boat, but where's the rest of the bridge? It's more magnified. And then you could have both, right? So here on the left, you have a smaller field of view with less magnification, and on the right, you have a larger field of view with more magnification. Does that kind of make sense, the difference between those two? Okay.
I have a quick question.
Yeah.
I know we are not supposed to, the point is not astrophotography, but
Right.
if we are talking about from a camera's perspective, there is no difference between field of view and magnification, right?
There is. Same thing applies. The question is about cameras and astrophotography, irregular photography. If you can see more, that's still a larger field of view. And if you zoom in, yeah, it's the same for cameras.
Yeah,
Yeah.
and so the field of view will be set kind of by the size of your optical path, right, and the size of your camera sensor, right? So it's one of the two will be a limiter, right? Either how big your camera sensor is, or some hole in the telescope.
Yeah.
Right? And the telescope optical path will be a limiter, right? And maybe not allow you to fill the camera sensor, right? I mean,
So yeah, Wolf was just saying that the size of the sensor and the size of the aperture determine the field of view, and different properties determine the magnification. But magnification is still independent from field of view, whether it's looking with your eye or looking with your camera. With your camera, if you've got the camera screwed onto the end of your telescope, it's not really going to change. Yeah, you're going to leave that thing fixed. Once you get it working, you want it to stay working, so you're going to leave it fixed. And so they may not change, whereas with eyepieces, you're swapping them in and out, and you're going to get these different characteristics more easily.
There's no zoom, as we say in astrophotography camera.
There is no zoom. The lens is fixed because it's your telescope. Okay, so magnification, how much? I think Wolf alluded to this at the top of the slides. More magnification is not always better. It depends on what you're trying to see. So some objects are really big, relatively speaking. And so if you zoom in on something that's really big, you only see a small part of it. So you might want to have a lower magnification or a lower power zoom out, so to speak. Yeah, and the more you zoom in to something, you might think, okay, great. So planets, for example, they're pretty small. Zooming in, we want to see more, that's great. So you might think, I'm going to put in as much magnification as I can so I can zoom in as close as possible and make the view of Jupiter take up the whole eyepiece. Well, it's not so simple. It doesn't always get that much better. You have trade-offs when you add magnification. For one, the image becomes dimmer because you have less light over a larger area, or the same amount of light but over a larger area, so it appears dimmer. And the other thing is that distortions in the atmosphere or the shaking of the telescope or you touching the telescope become more amplified when you are zoomed in that far. And so it can be difficult to get a really steady view as well. So magnification makes objects appear larger, but how large is large? So sizes of the sky objects are described using angular dimensions. These are degrees, minutes, and seconds. It's similar to like if you have a circle, right? The sky horizon to horizon is 180 degrees because it's half a circle. A whole circle is 360 degrees, right? If you're watching ice skating or snowboarding or the X Games or something and someone does a 360, they spin all the way around and come back to where they were. If they do a 180, they go halfway around. So similarly, the horizon is 180 degrees. And so we can chop up, that 180 degrees into smaller pieces, 179 degrees, or minutes or seconds, which are fractions of a degree. And then we can say, when we're looking up at the night sky at something, it takes up this much, and that is 3 degrees, or whatever it is. So for example, the moon is about half a degree of sky in size. So when you're looking up at the full moon and you see it, that is roughly 1/2 of 1 degree of the 180 degrees on the horizon. And the typical telescope view is around 80x magnification, which will affect how much, what angular size you are able to see through your eyepiece. So some more examples. So the Pleiades. This is an open star cluster. You can see it with your naked eye. It's really nice to see. It's great through binoculars because it's almost 2 degrees wide. Good magnification would be around 25x. Remember we just said typical magnification on a telescope is closer to 80. And of course, you can change that through changing your eyepieces and changing your optics. But we're looking at telescopes today, and those are, on average, higher magnification than something like binoculars, around 80x. And so if you want to see the Pleiades, you want to zoom out, so to speak, and get a good magnification of around 25x. Planets, as I alluded to earlier, like Jupiter, are really small, so they benefit from a lot of magnification. They're in the neighborhood of 0.01 degrees, or 10 to 50 seconds. That's a fraction of a degree. Typical magnification for Jupiter that is a good trade-off between size, details, brightness, and all of that is about 200 to 250x. And again, it depends on those seeing conditions, the transparency. If you actually zoom in that far, is the atmosphere stable enough to give you a view of that's pleasing. So let's talk more. Let's take a look at the Pleiades in more detail and see what it looks like through different optical systems. So here we have a Celestron C8, which is the same as that telescope over there and that telescope over there, both Celestron C8s. And here we have an eyepiece, which is an XL LX 25 millimeter eyepiece.
Hard to read, sorry. But
Yeah.
25 millimeter, 81x magnification.
Right. And so, as we learned earlier, if you want to determine the magnification, you divide the focal length of the telescope by the focal length of the eyepiece. So 2032 divided by 25 equals 81. And so here's this circle here represents what fraction of the Pleiades you're seeing when it's magnified by a factor of 81 times. And you can see, for context, in the corner of the full picture there, that's kind of the extent of the Pleiades, right? There's 7 main stars and a bunch of nebulosity around them, and you want to see a little bit around the edges too. But at 81x, you're seeing, 1, maybe 2 of those main stars, sort of at best. So let's try a different thing. Here's a refractor telescope with the same eyepiece, so different telescope, same eyepiece, but the focal length of this telescope is 1,000 millimeters, and the eyepiece focal length is still 25, so now we're at 40x. So this kind of zooms us out by a factor of 2 or half, and we can see more of the Pleiades. We still can't quite see the extents on the bottom of the nebulosity, and it's kind of just taking up the whole field of view, but we can definitely see more than we could see at the 81 magnification. So let's keep going out. Here's a different refractor, same eyepiece, but a smaller focal length on this refractor. So now this is the Pleiades at a factor of 29x. And now we're getting there, right? You can see relative to the reference image on the bottom left, or bottom left, it's almost the whole thing, which is great. So let's get better. Let's try to get more of that. Here's a same refractor as the last slide, but with an eyepiece whose focal length is 30 millimeters. And so that's a larger denominator, which means smaller result of 24x. And now we've got the Pleiades in full view, plus some of the background stars, which kind of puts it into context of like, yeah, this is a special thing because not everything looks all bright and fuzzy like that. There's actually a lot of emptiness around it. And so that's a good magnification. And you could continue this exercise with different objects. So here we're looking at the Ring Nebula at 24x, but you might say, what? What nebula? Right? These the big stars, right? They're actually bigger than the object we're trying to see, which is very tiny right in the middle. And so this is the Ring Nebula at 24x, right? So 24x, there's nothing special about it. It happens to be good for the Pleiades because the Pleiades are large. They take up a large angular distance. But the Ring Nebula is so much smaller. So let's zoom in a little bit. So here we have one of the configurations we saw earlier. At 81x, we've got the Ring Nebula. And I kind of like this for the Ring Nebula because it's still really bright, like especially if you're looking with your eyes. Again, these are photos, and so they're going to be better at what you see visually. It's still really bright. You still get a sense for the outside and the inside, and you can tell it's not a star. But if we have good seeing, let's zoom in more. So here we go at 170x. You can really clearly see the difference between the bright outside and the darker inside. You can kind of see this little dot here. There's a few little stars around it. And that might be the extent that you would want to go for this Ring Nebula, because if you zoom in more, it's going to get dimmer depending on your sky conditions. Seeing something that's really dim but huge is less interesting than seeing something that's brighter and a little bit smaller. Okay, so a rule of thumb for magnification. Your telescope can support, as in you will have an enjoyable view, roughly, for every 1 inch of aperture, about 50x magnification. So if you have a 4-inch telescope, you can go up to 200x magnification and expect to have a good view, good sort of subjectively speaking. And likewise, 25 millimeters per inch or so. So 2x of magnification for every millimeter of aperture. Actual limits, again, vary depending on all kinds of other factors, but that's a good rule of thumb. And given the sky conditions, like realistically speaking, your maximum magnification tends to top out around 200 to 300x. Even if your optics could support more beyond that, just what's going on in the atmosphere is going to be your limiting factor. But if you have an exceptional night, go as far as you can and see what it's like, and then back off. Maybe you'll make it up to 400x, for example. But don't be fooled by the old telescopes. Just because it says 500, those optics are not going to get you anywhere near what you'd like at a 500x. And even larger aperture telescopes won't necessarily do better when it comes to magnification because those sky factors become limiting, but it does allow you to view fainter objects, so more aperture is better in that way. Okay, let's talk about color. So you may have seen pictures of Jupiter from space telescopes or online or whatever, and you kind of expect it to look somewhat like this, where it's kind of mostly grayish, brownish, and reddish, and striped like that. But if you look through your telescope and you look at Jupiter and something's not quite right, you may see something like this. And often at star parties, if I have a little bit of chromatic aberration in my telescope, people look and be like, whoa, cool, it's blue, it's pink. I'm like, well, I might have a filter on there. It's not exactly what's happening. So what's happening in this scenario? So there are different sources of what we call chromatic aberration, just kind of the splitting of white light into that rainbow. One can be the optical elements themselves. The other could be the atmosphere. So maybe you remember prisms, and you remember how if light passes through a prism, the prism is, say, glass or acrylic in modern days, and light goes from the air to the glass medium, and then from the glass back to the air. And as that happens, the different wavelengths of light, the different colors that are actually hidden in that white light, split out a little bit, and split out a little bit more in this example. And so what looked like white light coming in actually looks like a rainbow coming out. And so this is a similar effect as to what happens from what can happen with our atmosphere, right? Our atmosphere can act like a prism because it's not the same consistent material from top to bottom. Space has no air, no water, right, at a certain point. But our atmosphere has air and water vapor and all kinds of dust and stuff. And so the atmosphere itself can do that sort of refracting effect on light and make the white light turn into its constituent components. And the closer an object gets to the horizon, the more light is refracted and the more its color components split. And that's because you can kind of see in this picture, right? And Swami and Wolf were talking about earlier, it's really great if you can look at an object that's straight up because you have less atmosphere to look through. There's less opportunity for water vapor to distort things or for the air to be weird. But if you're looking across the horizon, look how much more that is, right? You can kind of tell it's like 2x more, sort of like in this image, looking out across the horizon. So that's a lot more water that the light has to zip past and avoid getting refracted by. So those effects can amplify if you're looking lower at the horizon. Some more things. Resolution. So resolution is similar to what you might think of in like a digital image, right? If you have this huge 100 megapixel image and you zoom in and you zoom in, you still see a relatively sort of clear thing, you see separate objects. But if you've got a 1 megapixel image, right, and you zoom in, at a certain point you see the square of the pixel and you don't see anything else, within that square. And that's a similar concept when it comes to the light that we see through our telescopes, right? At a certain point, depending on your optics, the resolution doesn't get any better the more you zoom in. And so this is kind of illustrated here. Larger aperture telescopes provide higher resolution views. It turns out to be the only thing that matters when it comes to resolution is the aperture, which is kind of nice because everything else we're talking about, you've got the aperture of the telescope, you have the eyepiece, you have this, you have that. This is sort of one dimension that determines this. And here you can see a higher resolution image on the right-hand side and a lower resolution on the left-hand side. And this, by the way, is an example of one thing that's popular to do in this hobby, which is identifying and observing double stars, or sometimes people call them splitting double stars. So double stars are just stars that appear or are actually very close to each other in the night sky. And they can be really fun to see through the eyepiece because it's different from everything else we see. And in order to be able to split those stars, you need the right conditions, you need enough aperture. Otherwise, you might end up with kind of one elongated or one completely round star where there's actually a double star. So here's some examples of double stars. Epsilon Lyrae is a 5-star system with 4 visible stars, so you can sort of see how these stars are separated by 2.3 arcseconds, so a fraction of a degree, really tiny. These are separated by a similar amount, 2.5. And these tables below, you can kind of see where, what aperture you would need in order to resolve those into 2 individual stars, like on the previous slide. So you can kind of see that up here, you're sort of at 50 millimeter telescope. You're kind of at the maximum, you're kind of at the borderline here of whether you can resolve this. But as the aperture goes up, the amount of space that you can resolve between them goes down, meaning the resolution goes up, so you can see those finer and finer details. So you can see details of 1.93, 1.66, 1.36, smaller and smaller details as you go down. And so, in order to see this, you need to be able to resolve at least, maybe 2x or so what the actual separation is, just because things blur together, all those other effects kick into gear when you are trying to split these double stars. And so likewise in the inches world, 4 to 5 inches versus 100 to 130 millimeters will help you resolve these particular objects.
And for anybody who's like in engineering or electronics or signaling, like Nyquist sampling theory, right? It's almost like that a little bit, if that rings a bell to anybody, right? You have to like double oversample, right, to really see, to be able to resolve certain things. That didn't make sense to you, don't worry about it.
Okay, so more about the view, flatness of the field. So this is something that sometimes makes more sense when we talk about astrophotography, or it's at least a more desirable quality. But we can talk about it in visual observing as well. So it describes whether the inner and the outer parts of the field of view can be in focus at the same time. And so, the lenses that we're using, they're round. They have a curvature to them. Our eyes have a curvature to them. And so what happens is that light that hits those curvatures at different angles may appear distorted or out of focus, depending on the optics. And this is more important for astrophotography because when you're taking a picture, you can look at the whole thing at once. You can look at the sides, you can look at the top, you can look at the bottom with the center of your eyes, and you want to see sort of nice round stars everywhere. When you're looking through an eyepiece, it's a similar experience, but you're mostly focused in the middle of the eyepiece, and so distortions way out on the edges are sort of in your peripheral vision or maybe less interesting. And then you can always just nudge the telescope over if you want to see that better. So without any special measures, telescope's field is not flat, and you can sort of see the ray diagrams that attempt to explain this. And he's
One of the colors is not projecting well, right? You can't really see.
Blue and red.
Well, yeah, that's kind of what's meant to be it's almost impossible to see it as an arc here.
Oh.
Saying that really, depending on where the rays are, they're not all focusing on the focal plane here. They're actually focusing on this curve. But I know it's almost impossible to see anything on the projector, so.
Yeah, and we didn't
get the idea, right?
Yeah, and we didn't go a ton into the ray diagrams, and this is going to be in the extra content. But it's just to say that light focuses in different spots depending on the optical elements. And then there's assorted other issues. So other things you might come across as far as aberrations go. Coma is when the stars near the edges look like sort of these comets. And this can be due to physical issues in the telescope, if the lens is physically tightened or squished up against something, or if the lenses are not and mirrors are not properly collimated, then the light is not taking a perfect path to your eye. Astigmatism, vertical and horizontal axes can achieve focus at the same time, so you get something that looks a little wonky. Spherical aberration, more later about that, and others. So there are all kinds of artifacts that you may discover when you're looking through a telescope, and this hopefully gives you an idea of a sampling of those artifacts and to be able to distinguish them from the actual objects in the night sky when you're looking through your telescope.
Okay. Yeah, so I hope that kind of made sense what Carl went over, right? So I know it was a lot of stuff to throw at you, but all these terms like coma, field of view, splitting stars, these are all terms that some astronomer might throw at you when they're jabbering at you about their equipment, right? Or talking to you in the field. So it's good to know these terms, right? And at least I hope that you remember them and go, that sounds familiar, right? And you kind of know where to place it, right? And remember what it means. So now to kind of get us ready for the stuff that we're going to talk about after cookies, right? So remember that a telescope is a system of parts with 4 critical components, right? The optical tube, eyepieces, the mount, which had in turn like 2 subcomponents, right? The swivelly part and the tripod, and then the object finder, right? And you can see those in a moment. You can walk around, you can look at equipment. We're happy to talk to you about it, right? And we'll go through each of these, after the break. Then there's some subcomponents worth mentioning that we'll touch on: star diagonals and focusers. And there's a whole bunch of additional stuff that you may need, to go out and observe. So we want to make sure that you think of these things as you're putting together your telescope kit, right? And we visit these at the end a little bit more as well. But just to put this again all into context: optical tube, tripod with head, mount with head and tripod. And then here, hello, where are we? There we go, right? Eyepiece and finder. And then, here are the focuser and the star diagonal we'll just touch on as well. And then these are all these other things that you may also want to put on your shopping list or packing list, right? You'll want something that gives you some star maps, either on paper or electronically. Make sure you get some warm clothes. It always gets colder than you think it will. I just made that mistake last Friday. You probably want an observing chair, you want a red flashlight, something else to keep you warm. You may need a power supply, something called a dew shield. So we'll touch on all these things again later, but I want to just sensitize you right now, right? Make sure you think of these things also if you're going to go telescope shopping, right? Because otherwise you'll probably be out there in the field, feel like, shoot, this is not working. Either I'm freezing or I forgot something, right? And you don't want to be there. So each of these components, the optical telescope assembly, the eyepiece, whatever, they come in various types. We'll talk about those. And for a telescope to provide a good, enjoyable experience, really all of these components must work well. And that's often a failure of these department store kits, right? Maybe the optical tube is good, but the eyepieces are junk or something, right? And so you don't really get a good solution that way. So that's why we tell you to kind of stay away from those things. Telescope optical tubes come in 3 major types: refractors, reflectors, and hybrids. And they've got these funny names: dioptrics, catoptrics, and catadioptrics. These are kind of tongue twisters a little bit. For the most part, we call them refractors, reflectors, and well, I guess here I just call them hybrids to make it easy.
All right, so let's get started on the next section. And here we're going to talk about the different types of optical tubes, right? In the beginning, Wolf was talking about what are the different components of a telescope, and the most important component that we talked about is the optical tube assembly, the OTA, right? This is this one. There are many different types of optical tube assemblies. There are refractors, reflectors. Refractors are obviously made from lenses, reflectors are made with mirrors, and then there are hybrids which have a combination of lenses and mirrors in there. So we'll go over these in some detail and talk about the different types of OTAs. So let's start with the refractors, or also called as the dioptric telescopes, right? So if you remember our optical funnel, we talked about 2 parts, right? That's the optical tube assembly, and then there is the eyepiece here, right? And each of them has a lens in there. The optical assembly, I pressed the wrong button. All right. Okay. Yeah. So the optical tube assembly has the objective lens, and then the eyepiece assembly has the ocular lens, right? So here the light rays are coming parallel, and then we are bending them to a focal point, and then when they go on the other side, then we are making them go parallel again to enter our eyes. All of this, the changing of the direction of the light rays is happening using lenses, right? So any OTA that uses lenses inside to bend the light, that's called a refractor. Here are some examples of the refractor telescopes. Just a few pictures, and this is your typical diagram of a refractor telescope, right? The light is coming parallel in here. It passes through a lens assembly, it bends it, and it comes out on the other side, and it converges onto a focal point somewhere over here. Do you notice anything about this objective lens? Does it look like a typical lens that you would see?
Yeah.
Well, it's a little different, right? So you have this lens here, and then there is something else behind that, right? Yeah, so it's really a complex lens assembly, and we'll talk about why. So we talked about the prism effect, right? Where when light passes from one medium to another, it bends, and that's what the lens is doing. But how does prism work? Different colors or different wavelengths of lights, they bend at different angles. And so what happens is that if you just have a lens here and the light is bending, you see different colors are bending at different angles, so they don't all focus at the same point. And that's what we call chromatic aberration. So if you just use a single lens, it's going to be really difficult to get all the different colors to focus at one point. And so when you look at the image, you might actually see many different colors. Maybe not very distinct, but it'll be kind of blurred, but it will not be a very nice focused image. So what we do there is we add a second lens here behind the first lens, and that changes the direction of the light again. And the idea is to get these different color rays to focus at the same focal point. And so in a way, we are compensating for the different angles of refraction from the first lens. We compensate that by adding a second lens, and we get them to focus at the same point. So this assembly is called an achromat assembly, right? And or we just call it as an achromat doublet, because there are two lenses, so we call it a doublet. So but do achromats solve all the chromatic aberration problem? Not entirely, because they only help in converging the green and the red light. The blue and the purple, they are still focusing at a different point. And so the image that you see, it may have a little bit of a blue tinge or a purple fringe to it, right? So then what we can do is add a third lens, right? Over here behind this achromat assembly, you add a third lens, and that will bend the purple also, so that also focuses at the same point as the red and green. And so now we have three lenses in there, and that's what we call a apochromatic triplet. It's a triplet now because you have three lenses, so it's an apochromatic triplet. And that pretty much completely eliminates any chromatic aberration. So as you can see, just refractor, in your mind you might think, okay, we just put a lens and we'll get a refractor, but it really is a combination of lenses to get that. Okay. So here are some examples of how Jupiter might look like. If you view it through a achromat, right, you see there's a bluish tint to this, because the blue is still not converging at the same point. But if you use an apochromat, then it eliminates that blue, because that's also focusing at the same point, and you get a much clearer image. Now there is another way to correct the blue and purple fringes that we can get. We can add a filter to the eyepiece. Now filters are typically added on the eyepiece, right? What this does, what the filter will do is it will eliminate that blue from reaching your eyes. It's also called a fringe killer or apofilter, right? That may be attached to the eyepiece. So it eliminates the blue, and so you get an image which is not quite looking blue as this one. Right? But what is a filter doing? It's actually eliminating the blue light. So you're actually losing information, right? So it's not really as good as using an apochromat, because apochromat, you don't lose anything. It's bringing the blue back in, just getting it to focus correctly. Right? But it depends on your budget, because apochromats tend to be more expensive. Filters are typically not that expensive. So it depends on your budget, depends on on how comfortable you are with using a filter versus going for an apochromat assembly. So now in a yes.
Now quadruplets are coming, right? Quadruplets, 4 lenses are coming, right? Triplets, quadruplets, right? Where is the 4th lens going to be used in this case? Because there is no, everything is converging, there is nothing going out.
Yeah.
Where is the quadruplet coming?
I am not familiar with a quadruplet assembly. Are you?
I think, I'd have to check too, but I think in some cases it maybe to produce a flat field. So in some cases you add another element more for photography to get a flat field. So maybe that what you're thinking of?
Yeah, correct. Yeah, the flattener is not needed for those kind of stuff.
Yeah, right. So essentially it's a flattener kind of inside, I think. Right?
Inside,
Yeah.
okay, got it.
Yeah, so here what we're talking about is how to correct the chromatic aberration, right?
Yeah, sure.
Yeah.
Again, we're spending a lot of time today, but we can't cover every possible variant, right?
Yeah.
So there'll still be things we will not have shown you, just because we would be here a couple days.
Yeah.
Yeah. Yes.
If we add like a filtering lens for the eyepiece, does it also filter out the natural colors in the image along with the chromatic aberration?
It depends on the type of filter used. There are many different types of filters. Yeah.
But I think for this, I think the answer is yes,
Yeah.
right? Because the filter doesn't know whether the purple is from the chromatic aberration
Or
from
just
the
a
light
natural
that's coming
blue, yeah.
from the universe, right?
Exactly.
They have no idea, so they won't throw it all away. I think that's what you were asking, right? Yeah.
Okay. Okay. All right. So now let's talk a little bit about the quality of the refractor telescope, right? So what does it depend on? The lens structure and the shape, glass type, optical coatings. We'll talk about all of these in just a moment. So we talked about different types of lens assemblies, singlet, doublet, triplet, achromat and apochromat, right? So these will determine the quality of your refractor telescope. What's the type of glass that has been used to make the lenses, right? There are many different types of material that are used for making the lenses. The shape of the lens itself, right? Manufacturing of any lens or any optical material will have some defects in there anyways. So it depends on the quality of the manufacturing, right? How precise the curvature is, how uniform the curvature is, and so on. These lenses will also have some additional coatings on them. The objective of additional coating is to minimize reflections from the surface of the lens and to maximize the amount of light that's getting transmitted through the lens itself, right? The internal tube itself, the structure of the tube, there could be the paint inside the tube, and the internal structure in there. Sometimes you will have additional optical components inside the tube. So there are many different things that how the tube itself is constructed that can impact the quality of the telescope itself, and then the overall build quality as well. The alignment and the stiffness of the tube. So the many factors go into determining the quality of a refractor lens. Okay. Also, just a quick comparison of the refractors. Those were the original telescopes, right? Back in the old days when telescopes were invented and used, they were all refractors. And so if you compare to how the telescopes used to be in the old days and the modern refractor telescopes, the older ones tended to be long, narrow tubes. Primarily, it was very hard to manufacture big lenses and with good quality, so they would not be that curved. They were tended to be more on the flatter side, and so you could only make smaller diameter lenses. And so that's why the original refractor telescopes used to be smaller in diameter, and then if they're smaller in diameter, they are not bending the light that much, so they will end up being much longer in length, right? The focal length will be a lot more. Whereas the modern telescopes, they are much wider, the aperture is much larger, and they tend to be shorter length because the lenses can be manufactured in much larger diameter and with greater curvature, so they can focus the light in a much shorter distance. Right? And so they have, the older telescopes had high F numbers. We talked about F numbers earlier, so they had higher F numbers. The modern telescopes tend to have lower F numbers. Right. Just some pictures here of different types of refractor telescopes.
Actually, hang on, I'm sorry.
Yeah.
It's really hard to read on the projector for some reason, but maybe get some prices here, right? So this is a $300 thing. These are all 100 millimeter scopes, right? So they're all the same aperture. This one is $300. That one is $550. This one is $1,200, and that one is $3,000. Okay. So this is meant to show that there's a big range, right? And to some extent, you get something for your money, right? But this is where you need to know what you're looking for, what your budget is, right? So this is a doublet, for example. Sorry, this is the doublet here, right? This is the triplet from the same company, so you can see, it costs you almost twice as much to get the triplet, right? And then this is also a triplet, but this is on a premium. This is a premium brand, right? So you go from $1,200 to $3,000, right, for that premium brand, and they are really nice, right? So this is just to give you an idea of what the range is, right? And that's why you need to do some homework for what would work for you. Does that make sense? And I'm sorry, this is really hard to.
Yeah.
It turns out it's really hard to read on the projector for some reason, but these prices were just samples. Obviously, go look at them, right? Obviously, especially with tariffs, this could change, right? But you get the idea, right?
So Wolf, in terms of the performance between the two in the bottom,
Yeah.
are they both similar in performance because they have the same triplets and?
Yeah, it's a good question. So these are more mass-produced, right? These guys, they will individually figure each lens. You actually get a lens report of the quality of the lens. So they do spend more time, measuring and shaping the lens, right? So that it meets more precise criteria, right? And I have one of these things. It's really nice. Right? Now, I'm not going to tell you to spend $3,000 necessarily, right? And it may be good to go to a star party, and maybe you can look through both. Maybe people have, one of each, and you can see. For some things, it won't matter, but maybe you care. I don't know, right?
Might give you better viewing quality on one than the other.
Yeah, so two things like, will stars uniformly focus to really crisp points, right? And also, for example, chromatic aberration, right? Is it really color accurate, or do you get any distortions anywhere, right? Is the field uniform, right? Or around the edges, sometimes the image goes to crap, right? If the lenses are not high enough quality. So stuff like that. Does that make sense, right? Yeah. And sometimes you get super lucky. Sometimes you buy one of the mass market ones, and it's great, right? Luck of the draw, right?
Right.
Yeah, so just more examples.
Yeah, more examples, and again, some prices are mentioned there just for comparison. All right, so for refractor telescopes, we'll just what are the pros and cons? Like with everything, it has pros and cons. And we'll have similar pros and cons for reflectors and for hybrids, and then we can put them all together and compare them against each other. But just talking about the refractor telescopes, right? They're great for viewing planets. The modern ones, they have shorter focal lengths, so low F numbers, and these designs can provide wide field views, right? Even for larger star clusters and all, they're still very good options for observing. They are typically preferred in astrophotography, and they tend to cool down pretty fast. Right? The cons, of course, possible chromatic aberration if you're not using apochromat, and as we talked about, apochromat can get pretty expensive. So if you're not willing to spend that much money to get an apochromat, then yes, you might have to deal with a little bit of chromatic aberration. The aperture size is typically limited. They're not as big as reflectors. We'll get into the different sizes later on. But the most common sizes are like 4 inches or 6 inches. 6 inches probably the max for refractors. Although I think in some observatories they might have much bigger refractors.
Correct.
Also.
I was focusing here on the kind of stuff that
Yeah,
I could easily buy,
exactly.
Right?
Yeah.
There are larger refractors, but yeah, they get huge and super expensive, right?
Yes.
And not this kind of thing that you or I would
Yeah.
buy or carry around.
Exactly. And the lenses can be pretty heavy, right? And expensive too. And the last point, lower F numbers designs may require higher quality eyepieces also. So you may have to spend more on the eyepieces as well, because now you need higher quality eyepieces. Okay, let's talk about reflectors. Carl, are you going to talk about reflectors?
Yep.
All right.
Okay, so let's talk about reflectors. Okay, so reflectors, we're moving from lenses to mirrors. Lenses, especially large ones, can be difficult to make, as Swami said. Mirrors are an alternative. A curved mirror can focus light similar to a lens. And so, well, in a different way, but in a similar fashion. So you can kind of see that, I'll just put this a little bit like this. You can kind of see how we talked about the lens in great length, and it refracts the light, so it bends it beyond the lens and makes it to a point. The mirror, however, is a concave shape instead of a convex shape, and therefore it reflects the light back towards the source into a point. So both lenses and mirrors can focus light to a point, which is what we want for our telescopes. A parabolic mirror, it turns out, will always bring parallel light rays to focus, which is great. We want everything to focus in the same spot. And a parabolic mirror will do that just because that's how the math and the ray diagrams work out. But they are really expensive to make, and spherical mirrors do a pretty good job, and they're much cheaper to make. So most of the mirrors, I think all the mirrors we have on display here would be spherical mirrors. And of course, that's another differentiator that you might see in when you're browsing different reflector models. If the mirror has a more parabolic shape, then you will pay for that. So, like we were saying, the spherical mirror, light does not focus exactly to a point. It focuses more to an area, depending on what angle, where the light is hitting the mirror. And so this kind of illustrates how the spherical mirror and the parabolic mirror behave differently. Where the parabolic mirror, everything hits a nice single point, and the spherical mirror, they get to the same region. But it turns out the more that the less curvature that you have. So if you imagine a sphere, right, like a ball, most mirrors are just a ball. If you have a tiny ball, then it curves a lot, right, or in any given distance. If you have a big ball, or like a beach ball, right, in any given distance, it's curving less and less, but it still creates a sphere. And so with that lower curvature, that effect goes down. This effect of that spreading of the light goes down. And so it approximates a point. And that's good enough for us for a lot of cases. So for a given aperture, a mirror requires less glass than a lens. It may be less massive and therefore lighter than a lens. And it only has one surface that needs to be shaped, right? The lens is sort of convex on both ends, and so you kind of have to take that glass and make that shape on both sides of the lens. The mirror can be flat on one end. It doesn't care because the light's not going through it. It's bouncing off of it. You just need to shape the one side of it. And because light is just bouncing off the mirror, right? It's not going through the lens, changing mediums and having the light rays refracted. There's no prism effect. So reflectors, therefore, do not suffer from chromatic aberration, which is great. We don't want chromatic aberration. But there are still some unique challenges to reflectors. Because the light is focusing back towards the source, the natural question to ask is, where would you put your eyepiece? You can't stand in front of the telescope and block the light from what you're trying to see, so we have to do something different. Like I said, with the refractor, the light goes through the lens, and so you can have the lens in front of you, and the light will come in behind you naturally, because that's what lenses do. But the reflector needs a trick. And so, for example, this reflector on the bottom uses a second mirror. And you can kind of see the telescope is pointing off this way to the left. If it's looking at a celestial object, or maybe a terrestrial object right over to the left, then the light from there is coming in to the tube, and it hits the mirror on the back, on the right side of that image. And then if that spherical but large curvature mirror focuses that light mostly to a point, and it hits this secondary mirror, which has this neat little angle that bounce it off, flicks it off here to the side of the tube. And we can put our head over here without obstructing the light path that we're trying to see and the path that it takes. So that's one trick. This reflector design is called a Newtonian reflector. The diagonal, also known as secondary mirror, it's another mirror that sits at a diagonal, hence secondary diagonal mirror. It does get in the way of that light path a little bit. I mean, you can sort of see it's not completely blocking it. We'll talk about these fins in a moment. But it is taking a chunk of area away from the total aperture of the telescope. And so that reduces the effective aperture of the telescope. And there's a trade-off to make with how large this secondary mirror is, how much light it can reflect back into the eyepiece, and how much of the whole aperture that it is obstructing. And so a typical trade-off is around 10%. And because you're getting less light, you have those the effects of having less light, for example, loss of image contrast, which I was telling you about earlier. So the secondary mirror needs to be held up by something, right? It can't just float in the middle. Maybe you could use magnets or something to make that happen. That might be cool. But it doesn't. In practice, it doesn't. And so it's held up by a truss of these vanes or these spider support mechanism. And so because these also have to go into the light path, they also obstruct the aperture a little bit, but they cause an additional effect which, depending on who you are, may or may not be desirable. Those lines actually do cause a bit of diffraction of the light. And so that just means that those lines effectively show up as in the image that you see either with your eye or especially through a camera as these spikes. And so we call these diffraction spikes because that's the physical effect that's at play there. And if you grew up looking at Hubble telescope images and now Webb telescope images like I did, you're used to seeing these, right? You're used to seeing some big, beautiful view and stars with these little crosses on them, and it looks cool. Or Webb has three vanes connecting it, and so I think it ends up having 6 diffraction spikes. That's how that works out for some reason. And so you would see, not just 4, but you'd see kind of like 6 of them. And so I'm used to seeing that, so I kind of like that effect. But it is technically an optical, defect of sorts. Yeah.
Are those spikes even visible when you're visually observing?
It would have to be a really bright star. And as you can sort of see in this image, as the slide says as well, these fainter stars, I mean, you can't really see them. This is obviously an image taken with a camera, but you can't really see the spikes there. As the stars get brighter and brighter, the spikes get more pronounced.
Another question. So,
Yeah.
so since the smaller mirror is sitting in the middle,
Uh-huh.
does it obstruct any view or it does not?
It does. Yeah, it definitely does.
I know it
Oh.
reduces the amount of light
Oh, yes.
getting in, but does it obstruct the view?
So it turns out no, because we live, this is my explanation, you guys can correct me if I'm wrong, but light, so we have an atmosphere, we have air, right? And you might notice that like, if you're looking at me at this light, I have a shadow, right? But it's not completely black behind me. You can see behind me. If I were on the moon, right, and I had the light shining on me, it would be completely black because there's no air to kind of bounce the light and create light in that shadowy area. So I think that's the same effect that's in play here, right? The light can kind of sneak around that due to various effects. Does that answer your question? Yeah.
I guess the answer is that it does not obstruct the view.
You won't notice. Yeah, you won't see a hole in the middle.
I see. That's my question.
It may be dimmer, but again, it's designed to only be a 10% obstruction, and so you probably wouldn't notice. Do you have anything to add?
I think one way to think of it is, right, if we're looking at a star,
Yeah.
right? I mean, a star is super far away to the point where to us it looks like a tiny dot, but it's still huge, right? That star is still out there, way bigger than anything you can imagine. and it's way bigger than your aperture, right? So it is sending a whole bunch of parallel light rays, towards us. And if you put an obstruction there, so okay, some of the rays of the star will be blocked, right? But other rays of the star actually go past it, and you still see the star. Does that make sense?
Right. Yeah.
So there's some light loss, but yeah, you don't see a hole in the star. I know it's a great question actually, right? You can even try this yourself if we do solar astronomy on a Sunday afternoon here, right? And people sometimes basically ask that kind of question. But if you point this at the sun with proper filters, and if you cover half the telescope, the image does not show half black. The image just gets dimmer, if that makes sense a little bit, right? Because you're still seeing the whole sun in a way, you're just seeing less light. So we'll leave it there. We can talk about it more. I know it may be counterintuitive, right? But that's basically what happens.
Yeah.
So, okay.
Yeah, sounds good.
Telescope's more about light than image, basically.
So, I'm sorry, I didn't quite.
Telescope's more about letting in light than image.
Yeah.
Right,
The
right.
light source go like right here, really close. Then of course the entire light source might be covered up, right? So, but in practice, all the things we're looking at are so far away that effectively that obstruction doesn't obstruct the object, just a little bit of the light. So I hope that kind of works. Yeah.
So we're talking about reflectors. There are actually different kinds of reflectors, right? We discussed a Newtonian, and there are other kinds of reflectors, and they would require different mounting options. So with this setup, the aperture tends to be limited to about 8 inches because of the way that we're mounting it onto this equatorial mount. You can see the tube is fairly long. Of course, the diameter gets bigger, which means it gets bigger and heavier, and that's harder to support on a tripod with a particular mount style. But we can go bigger using a different mount style, and one way to do that is to have a Dobsonian telescope on one of these sort of rocker pivoting mounts. So the Dobsonian telescope in general, it is still a Newtonian reflector. You can tell because it's got the eyepiece poking out the top. And so there's a diagonal mirror secondary here. There's diffraction spikes and all of that jazz we just discussed. However, you can sort of see that it's mounted straight to the ground, right? It's not on one of these tripods like the Newtonian, and it's not on this sort of mechanical head that rotates around. It's just kind of on this platform and is supported by this mechanism here. And so this allows the telescope to get bigger and bigger because you don't have to hold something way up here with giant counterweights. You can just plop it on the ground and you can swivel it. You might need a ladder or a step ladder or a bigger ladder depending on how big it gets and where you're pointing. But it does allow you to scale that way. It's called a Dobsonian because this style was conceived by a man named John Dobson in the 60s. And particularly, it can be fairly inexpensive to build. Like I was just talking with someone about how this type of telescope, which we have back there, is something that you can construct yourself with a little bit of ingenuity. The tube itself doesn't really matter. You could use a cardboard tube, like a sonotube, like the kind you would use to pour cement pier. You can get at Home Depot. And then the mirror, of course, has to be, figured to be that spherical type of mirror for collecting light and reflecting it. But that's kind of the expensive component. But then, this is just wood and plastic and mounts and stuff. So you could conceivably put this together. And that was one of the goals, I think, that Dobson had in designing this, was to make it less expensive, more accessible. You don't have to have a big fancy telescope manufactured in a factory. You could make your own and still see awesome stuff. Or you can buy it too. And so then you can take this and keep getting bigger and bigger. And here you can kind of see a similar style reflector, right? Mirror here, secondary mirror, and eyepiece up there. So Dobsonian, Newtonian style. But it looks like it's missing something, right? It looks a little exposed here. Instead of having a tube, there's just this truss system, these supports here that hold it up. And it turns out that you don't really need a tube. Advantages are that it will block some stray light, and so you can kind of see there's a box down here that sort of protects the main part of the mirror from any light like right next to it. But that's just an extra thing that's big and bulky and doesn't really collapse. And so if you're transporting this large thing in your Honda Civic you might want to be able to take it apart and then put it back together in the field rather than having something that's 12 feet long and has to hang out the end of your car or something. And so some of these are really cool. They can kind of pack up into this neat little box, which is just sort of the dimensions of the mirror itself with a little bit of height. And of course, you could throw like a fabric shroud over this too. That would do a decent job of blocking stray light, and you could just roll up and stuff in the back seat. Yeah, so I think that covers that slide fairly well. So this particular Dobsonian, for an example, to give you some data points, is a 5-inch mirror, but it collapses down to 14.5 inches, I guess, as a little box shape, maybe 14.5 inches tall. So you can shrink this thing down to transport it more easily. I suppose this is the tube, so you probably disconnect this and just slap the tube together, and then you've just got this little bucket you're carrying around, and then you assemble it, and you've got the larger telescope. It weighs about 14 pounds, and you can set it on a tabletop. And so this, shows you how something like this can be inexpensive and portable, but you still get a 5-inch aperture, right? A 5-inch refractor, and we don't have one here. Yeah, because it's big and it's expensive and heavy and stuff, and it needs a mount like this one over here. But this is portable, and you get lots of aperture for your money. All telescopes, any optical system, requires you to align all the optical elements in order to achieve the right result. And we call this collimation. Reflectors are particularly susceptible to it. Refractors are typically collimated in the factory because they basically have the lens, and they might have another lens in the back or a mirror in the back or something for this. But they are more figured in the factory, and they're sort of cemented in place. They're not going to change. But this secondary mirror in particular on the reflectors is subject to a little bit of wobble, and therefore, depending on the telescope type, Newtonians in particular, you have to sometimes adjust the position of these mirrors in order to make sure the light all focuses in the right spot. So Newtonians, for example, may require the mirrors to be collimated more frequently, but it's not necessarily that difficult once you're used to it. And like I said, refractors collimated at the factory, you typically would never collimate a refractor unless you're Larry and you get a broken one from someone during Fix-It.
I do a lot of them.
He does a lot of them, yeah. So quick pros and cons. Reflectors, large apertures, we saw that. No chromatic aberration because they reflect, not refract. They're good for viewing deep sky objects because you can get such a large aperture. They're lighter, less expensive to build than refractors. The open tube, so if you get rid of the tube and you just have that truss, allows the mirror to reach ambient temperature, which is important for getting rid of optical aberrations. The refractor is always in a tube, and so it may take a little longer. The Dobs are light and tend to transport fast, and they're easy to set up. Cons, of course, you have that central obstruction, so you're losing some percentage. We said about 10% of light from your total aperture, but you get bigger aperture anyway, so yeah, pros and cons. You have the diffraction spikes, which could be a pro or con, depending on what you're used to. They can be bulky, right? But you can offset a little bit with the truss design, make something that collapses into a box. The low F number may require higher quality eyepieces, so that's what Wolf was alluding to when we're talking about the F number and how easily light, how forgiving the light can be focused with the higher F numbers versus the lower ones. And then, yeah, if the eyepiece is way up here, then you might need a ladder to get there and some stability. And the collimation is something that you will definitely experience. Yeah.
So you mentioned in the slide that for fainter objects,
Yeah.
so it's pro, right? But then you're actually losing
Yeah.
light by having the obstruction there.
Right.
So how does that?
So it goes, yeah, it's a good question. So you want more light, but you have the central obstruction. So is that really a pro with these reflectors? And it depends on that overall area. Remember, Wolf was talking about the area. That's the thing that is telling you how much light you're collecting. And so if that area of the big circle minus the area of the little circle, again, it works out to be like a 10% difference from the area of the big circle, is larger than the area of than the diameter of the aperture of some refractor, yeah, then you've got more light. So the numbers do matter in that sense. Yeah, it's true. Okay, so let's talk about some hybrids. Popular telescope design is this Cassegrain design, in which we have three examples of around the room. These are sort of characterized by being shorter, more squat tubes. And you can kind of see the light path that these take. So they are reflectors, but like I said, they're also hybrids, which we'll get to in a minute. But you've basically got a mirror here, it's familiar, the primary mirror. I think these are all 8-inch mirrors that we have in the room. And then you've got a secondary mirror. And then you've got kind of a hole in that first mirror so that the light can focus, light can go through that hole and focus to a point behind that primary mirror. So you get to stand behind your telescope again, which is great. No ladders required typically. And so you can sort of see how the light passes through this tube 3 times, right? Once on the way in, a second time going up to the secondary, and then a third time going back through. And so that focal length that we were talking about earlier, if you have a refractor, that focal length has to be contained within the entire length of the refractor. In this Cassegrain design, the focal length is the path that the light is taking here after it bounces off the mirror is sort of cut in half, right? Because you're going up here and then you're going back. And so this length plus this length contribute to make up the focal length, right? And so for that reason, the tube can be shorter. Does that make sense? If you had, if I only went one direction through the tube, you would need, and if there was a lens like the refractor, then you would need to wait the whole time for the lens to reach that point, for the light to reach that point. But here, because the light is bouncing around, we could take this to an extreme and bounce the light around back and forth, back and forth, back and forth, back and forth, and make a really short tube. It's just the distance that the light travels after it hits the mirror. And here, since we have this kind of zigzaggy design, we can make that distance of the whole assembly shorter. Hopefully that makes some sense. So these are great for amateur astronomy. They're very versatile. They come in different variants. 2 common ones are the Schmidt-Cassegrain. All of these ones I think are Schmidt-Cassegrain telescopes. And then another one is a Maksutov-Cassegrain. Both of them use spherical mirrors for simplicity. And there's another element, which we'll show in the next slide a little bit better. In the front of the telescope, there is actually a very thin lens of sorts that helps to further correct the light. So you have this spherical mirror, right? It doesn't focus perfectly to a point, as we showed in earlier slides, but this lens at the top of the Cassegrain telescopes helps to sort of counteract that. So this mirror lens hybrid designs make them catadioptrics, combination of the 2 Latin words that we've seen so far. So the difference between a Mac and an SCT, or a Maksutov Cassegrain and a Schmidt Cassegrain. In the Maksutov, the corrector plate has a spherical shape. The secondary mirror tends to be directly, which one is it? On the actual glass itself. So like here in the Cassegrain, you've got this kind of other mirror that is kind of like hanging out there. It's bolted onto this plate. Here it's actually, if you look at one, it looks pretty cool. You've got basically see-through glass and then silvered mirror in the middle, and it's one piece. And this design is often used. It works well, all things considered, for designs with a 6-inch aperture or smaller. Whereas the SCT can get bigger. It has a corrector plate that has a special aspherical shape. So this diagram, you can kind of see the difference between these 2 shapes. And the secondary mirror is attached to the corrector. So there's some bolts here that actually bolt on that mirror. And this design is typically used for larger apertures. So very similar, but slightly different designs. And here you can kind of see a 5-inch Mac with that shiny middle part. That's the mirror, actually silvered directly onto the glass. And then here you can see an 8-inch SCT where there is this thingy that essentially is the mount for the mirror. that just goes through a hole in the glass. So Cassegrains also have central obstructions, and so do Macs. In Macs, the secondary mirror is held by the corrector itself. It's silvered onto it, right? And so you don't need any of those spider veins so you don't have diffraction spikes. And again, central obstruction, you lose some contrast. But even in the SCT as well, you can sort of see there's no truss that holds the mirror. There's this little mechanism here, but it's kind of in the middle. So again, no diffraction spikes. And here are some alternate views of the SCT. You can sort of see it from, if you look straight down into it, which you can do in the ones we have here in the room, you can kind of see, yep, there's glass here, mirror here, and then you can see even this plastic tube sort of jutting out from the mirror, which is the hole that the light travels through, bouncing off the secondary mirror. And some more examples. There are prices here. I'll read them to you. So this is a Celestron C6, so 6-inch SCT, $840. Again, relative to a few years ago prices. C8, $1,350, and then a C11, $3,200. So you can sort of see how that price increases with the aperture size increases. Yeah, it says that these are from August 2024. So these prices. And then here you have an additional factor. So these are SCTs, 6, 8, and 11. These are SCTs, 8 and 11. But this 8-inch SCT is $1,600, and that 8-inch SCT is $1,350. So what's going on there? As Wolf alluded to earlier with the refractor example, they have different optics. And the Edge HD is used largely, you can use it for visual or photography, but photographers like this one because it has that flat field out to the edge, which is I think where the name comes from. And so the 11-inch Edge, $4,400 versus $3,200, so you get that flat field, those better optics. And then you want to go to 14 inches with an Edge HD, you're talking $7,500, which is a chunk of change. And then SCT telescopes, again, more examples, more prices. So this is the one that I have right over there. In 2024, it was, this is the 6-inch version, sorry. So this is about $1,100. The 8-inch version is the one I have over there. It's about $1,600. They do this trick, the $99, $1,599. $2,199 Celestron Evolution is sort of the next step up from this. So I think Wolf has the mount in that corner over there, the Evolution mount. And then here you have the CPC 800 GPS XLT. So there's a lot of things going on in that name. And it's more expensive, right? You can see it has this double arm fork mount. So we call these we call this like a fork mount. It has 2 arms and you kind of stick it in and it's supported on both sides. So it's a heftier mount. GPS, I guess, has probably got some technology to tell the mount exactly where it is with a GPS signal, which is important for aligning. XLT, I think, is the coating on the glass in First Celestron. They have some super anti-reflective coating, which gives you better views. And then, yeah, more examples. And then a quick thing about mounts, which we'll talk a lot more about later, but here are similar scopes but on very different mounts. And so we talked about this being a fork mount, and then this is actually an equatorial mount. And so in the fork mount, it's moving kind of left to right like this and up and down like that to point at the thing you want to look at. With an equatorial mount, it's actually rotating in 2 axes. And one of those axes is aligned with the axis of rotation of the Earth so that it can track, and it would, you point to something here and the sky appears to rotate this way and the mount rotates with it at the same rate. And so what you're looking at remains in the exact same position and the exact same orientation for as long as it's tracking, which is great, especially for photography. In my opinion, the equatorial ones are a little bit harder to use visually because it's easy for me to go point over there, but if I have to rotate there and then rotate this way to point, it's just harder for my brain. So pros and cons. Cassegrains allow for larger apertures than refractors, along with other reflectors. The Cassegrains are short, as we talked about, because the light bounces more throughout it, so you can make the total tube shorter. They're lighter and less expensive than refractors for the same aperture. Again, an 8-inch refractor is going to be hard to carry. No chromatic aberration, no diffraction spikes, good for viewing deep sky objects, good for general purpose scopes. They're quite versatile. Cons, compared to the Newtonian, they're more complex, so more glass, more potential light loss, more things that can go wrong. They're more expensive than Newtonians, and they can be heavier. But then you do have aperture loss to central obstruction. I think in the STTs it's a little bit bigger than the secondary mirror in Newtonians. And then the field of view is often smaller for these because these have a long focal length, and that also affects the magnification, and it has a factor in the field of view. And the closed tube design means that if you need the optics to cool down, which is typically what you want, it'll take longer because everything's all insulated and sealed up than compared to that open truss where everything's just exposed. Okay, is this the end of my spot?
Yeah, I can. We can transition here. So you can use it as a reference later, right? This kind of summarizes the 3 flavors of optical tubes again, right? And I hope you got out of this that there's a lot of trade-offs, right? So again, there's no single best answer, right? Trade-offs in cost and weight, right? And field of view, things like that, right? So I hope that that's a takeaway, right? You can walk out of here with, right? Okay, so I want to talk a moment about eyepieces here before we take another cookie break, okay? Because like we said, the eyepieces are tiny lenses compared to the big aperture lens, right? But they're really half of the optical system. And there's some related components like Barlow lenses, focal reducers, star diagonals, and focusers. And some of these I'll skip over today, and there'll be some content in the video that I mentioned. All right. So yeah, it's time for the second part of the optical system, right? We've had this diagram multiple times. We were just talking about, basically the optical tube that's effectively this lens, right? In some cases, that lens is multiple lenses or a mirror, right? But the optical tube is this part. And now we're here, right, talking about the eyepiece, that second bit of the optical system. So an eyepiece is always an assembly of one or more lenses in a housing. In my diagram on the prior slide, it was a single lens, right? But just like we talked about refractors, really it's 2 or 3 lenses, right, for the achromat or apochromat. Eyepieces also get more complex when you try to get fancy with them. And so yeah, just like with objective lenses of refractors, eyepieces, and their lenses, they vary. Number and arrangement of lenses, glass type, and overall, build quality. Okay. So these are just some diagrams to give you a feel, right? This is the prototypical eyepiece, like we've been drawing it in the basic funnel diagram. But man, you can tell they can get really complex, right, with a lot of lens elements in there. And these different designs create trade-offs between price and field of view and eye relief. One of you, I was talking about eye relief earlier. I forgot. I think we were talking about it, right? And you'll see that again in a second. All of you will see what that means. So we'll talk about some of these these trade-offs here. So barrel size. This is a really easy one, right? Does the eyepiece actually fit your telescope? There's not just one size fits all. Technically, it's 3 sizes, but for all practical purposes, it's 2 in our world. We'll see that in a second. Then we said focal length, of course, is an important property, right? Because that determines the magnification, right? Remember, we calculated magnifications earlier for some examples. Then field of view is a question. This thing, eye relief, and something called exit pupil. So let's touch on these. So barrel size. So eyepieces come in, in our world, it's mostly 1 1/4 inch barrels and 2-inch barrels. Some really cheap scopes have these tiny ones, but honestly, I haven't seen one of those in ages. So essentially 1 1/4 or 2-inch barrels. And there are devices that allow you to put the little one in a big hole, basically. So you can use the smaller eyepieces in a telescope that has a 2-inch slot. Quick review of field of view and magnification. Remember, right, this was same field of view, but more magnification. And this is same magnification, but bigger field of view, right? I hope that looks familiar from before, okay? And so, how does that kind of map to eyepieces? So an eyepiece on its own has a property called the apparent field of view, or AFOV. And then that AFOV combines with the telescope system, the rest of your scope, to form what's called a true field of view, or TFOV. Okay? And basically, the true field is the apparent field divided by the magnification. So again, a little bit of math, but not too bad. And the apparent field of view of different eyepieces typically varies between like 50 and 100 degrees. Okay, and that's one of those things that you get for having like more lens elements, like those really complex pictures on that earlier slide, get you to these big fields of views. Basic eyepieces usually are in 50 to 60, right? This is probably where you're going to spend your money when you're getting started. A couple examples. So recall angular sizes of some objects, right? We said the moon is like half a degree of sky. The Pleiades, we said like 2 degrees, right? Pretty big. And planets tend to be tiny, really small angular size in the sky. So if we want to look at the moon, right, and let's say we have an eyepiece with an apparent field of view of 60 degrees, our magnification is 80. That means our true field of view is, we get from this division, and the true field of view, the image circle that you see in your scope, gives you 0.75 degrees of sky. Does that make sense? Right? And so since we said the moon is half a degree, great, it fits in there perfectly, right? with some space around it. Now, if you had a more expensive eyepiece that gave you 100 degrees of field of view, apparent field of view, right? You could crank up the magnification to 130 and it would still fit in your image circle, right? Because basically, this here gives you a larger image circle, right? So you could zoom in more and still see all of it, right? So they're like these two different metrics, right, that are interacting here, field of view and magnification. For the Pleiades, if we have an eyepiece with 60 degrees and a magnification of 25, okay, that also kind of works, right? I end up looking at about 2.5 degrees of sky, in that image circle I see through my scope, and the Pleiades would fit inside. Okay. For Jupiter and Saturn, if I have a 60-degree apparent field of view eyepiece, let's say 200x magnification, I get 0.3 degrees of sky, which is actually huge compared to that tiny planet, right? But keep in mind, when you look at planets, you usually want to see the moons around it too, right? So you do want to capture more, right? We're not just trying to zoom in on that giant, tiny planet. And like Carl was saying earlier, even if you did zoom in on that planet like crazy, it probably would look like crap, right? Because too much magnification is not helping. So here's some examples, right? Basically, yeah. So this is kind of what we said. This is essentially, here it fits, the moon fits with some margin. Here, I've zoomed in, basically too much, right? With that same field of view, right? And we're just seeing a chunk of the moon. Maybe you want this if you really want to look at craters, right? But these are all trade-offs to think about when you try to go eyepiece shopping or what. Hello, do you want to join us? Yeah, come on in. Man, this is hard to see on this slide. I'm sorry. Okay, maybe we'll not spend too much time on this slide, but you can see essentially, it's not focused well, right? But Jupiter's in the middle and the moons are around it, right? And you probably want something where you zoomed in enough and have enough field of view that you can see the planet and moons around it. Yeah, this slide is terrible. It's really hard to read on the projector. Okay, eye relief and exit pupil. So I mentioned those properties earlier. So eye relief is this dimension basically in the diagram, right? So here is a lens, and it turns out there's kind of an optimal place for your eyeball to be sitting, right? So that you can see a good image as intended. And that distance from the lens to your eyeball is called the eye relief. Okay. And a larger eye relief may be required if you're wearing glasses, right? So I take my glasses off usually for observing. My prescription is such that I can get away with this. If you cannot, right, if you have some astigmatism or something else, right, where you just have to keep your glasses on, you got to be able to fit your glasses in between here, okay? And so you want to make sure when you buy eyepieces, you buy an eyepiece that has enough eye relief to allow that. Does that make sense? Yeah. And then another property here, then the other one is the exit pupil. It's basically is how wide is the light bundle there, okay? And ideally, you want this bundle to be matched to your pupil size, right? Because if this bundle is bigger than your pupil, light is again lost. Does that make sense, right? Because light will just hit the around your pupil. Or if this light bundle is really tiny, in a way, then you're wasting part of your pupil size, right? So ideally, you want these to be as closely matched as possible, right? And then you maximize kind of your light collection. Yeah, like we just said, so if eye relief is too small, eyeglasses may not fit. If the exit pupil, is really small, right, then some of your pupil's capacity is wasted. Now, if everything else is equal in terms of an eyepiece design, more magnification means that your eye relief and your exit pupil shrink, right? So that means if you have basically the same type of eyepiece, higher magnification means, yeah, it may be harder for you to squeeze your glasses in between, right, if you have to, that kind of a thing. Okay, let's see. So optical imperfections, right? Swami talked some about, like refractors, right? Different lens, different glass, can give you different properties, a different quality of refractors. The same thing is true here with the tiny lenses of the eyepieces. So, if you end up with, suboptimal designs, your image may be sharp in the center but blurry towards the edges, or the contrast may be poor. Remember, Carl showed contrast, right, where the object might be sitting in a white milky field as opposed to black space, right? That can come from crappy eyepieces, among other things. Glass and coatings matter, and these all, factor into the price of the eyepiece, right? And like we said multiple times, high F-number telescopes are more forgiving. If you buy a low F-number telescope, you may have to spend more money on eyepieces, otherwise you'll have a mismatched system, and you're actually not going to get the benefit of your nice refractor or whatever. So trade-offs also include physical size and weight. Eyepiece weight can range from like, 1/10 of a pound to 2 pounds. Some of these things are huge. And the heavy ones tend to be the ones where you have a really wide, field of view. So they're great from the field of view perspective, but they can be super heavy. And some scope mounts will actually start to fall over if you put such a heavy eyepiece in. And again, price range can be huge, right? From a few tens of bucks to $1,000. Although, again, don't panic with that $1,000 price, right? If you're getting started, usually 50 to 100 bucks will buy you a really nice eyepiece, for all practical purposes. Here's some examples of eyepieces. These are both 12 millimeter, so same focal length. But notice this one has 50 degrees field of view. This one has 60 degrees apparent field of view, right? So extra money buys you more field. Eye relief is 8 millimeters here, 16 millimeters here. So again, more money buys you, space to put your glasses in between, for example, right? I hope that makes sense. Again, just more examples. That again, all 12 millimeters or thereabouts, going all the way from $30 to $630, right? So this is one of those super wide field eyepieces, right? It has a 100-degree apparent field. So these are really nice. The money does buy you something. You look through and you kind of feel like you're in outer space. It's almost like you have your nose pressed against like a porthole in a space station, right? Because it feels very immersive, but you got to pay for that immersion. Okay, that's just another example of the field. Let me skip this one here in the interest of time. There are things called zoom lenses, or zoom eyepieces, excuse me, right? So, for the indecisive, or if you want to have something that's super easy to carry, right? You don't want lots of loose pieces. You just want to take one thing because you're space constrained. You could buy, one of these things, and it has adjustable focal length from 8 to 24 millimeters. Price difference is $290 to $80. So again, you get something for your money. Quality is better. Optical quality is better over here. Field of view is larger. But zoom lenses can be pretty good. But all else being equal, single focal length eyepieces will typically give you a better quality, right? Because there's always a trade-off. Nothing's ever free, right? So you get the zoom capability, but it's probably losing some quality in some other places. Just one more word on, I guess, these hand grenade-sized, really heavy eyepieces. They tend to be super expensive, like we saw, $630 in one case. Super heavy, may cause your mount to tip over. Eye relief may be low, right? So if you need glasses, don't buy these too quickly. Depending on your telescope, your telescope might actually be the limiter, right? You might not get the expected field if some other part of your scope is limiting it. Okay, so it's also important, right? So you don't want to spend too much money on these things too quickly if you're not sure this is really a good fit for you. But if it is, man, these things are great. There are some specialty eyepieces for specific use cases. This is called a centering eyepiece. We'll meet this again when we talk about mounts after the cookie break. There are also these fancy digital eyepieces. I don't have one of these. Some people like these, right? Like night vision eyepieces, light amplifying, fancy stuff, right? Nothing you need right now. Just want to let you know these things exist, because you may bump into them in your travels. Okay. There are things, I'm not going to go into detail on Barlow lenses. There'll be some more content in the video, but I want to quickly mention it. So there's a thing called a Barlow lens, and it's something that fits in between the eyepiece and the telescope, and it effectively increases the magnification, right? So a Barlow lens reshapes the light path, so it effectively increases the focal length of the telescope, and then if we do our magnification division, right, it turns out that it effectively increases magnification. So Barlow lenses come in configurations like 2x, 3x, so that basically if you add something like this, it doubles your magnification, right, or triples. Yeah, so this is what they look like, right, and they would go in between the scope and the eyepiece here. There's kind of the inverse thing. There's something called a focal reducer. It reduces your magnification, right, or reduces the focal length of the telescope effectively. And they come in handy if you want to see larger field of view objects, like the Pleiades maybe in some telescopes, right? Maybe you add a focal reducer. And it, and looks like these look like this, and you would stick it basically in this position on the telescope right there. Okay, and there'll be more on this stuff in the video if you want. So there'll be some more examples of how these things work and what you have. I just want to add here that we talked about flatness of field earlier, right? So if you go shopping for a focal reducer, it may get confusing because you may see flattener, reducer, reducer, flattener, right? So they all look similar. If you just look at the component, you can't necessarily tell without reading the details. So for visual use, the field curvature is not that important, right? For photography, though, you typically want the field to be flat. So photographers, right, will tend to buy these things that are, either just a flattener or they are reducer flatteners. Some are both, right? So you may have a component like this that is just a flattener or a reducer flattener for photography. If all you want to do is visual, you probably just need a reducer only, right? So you don't want to pay for something you don't need, right, necessarily. So you can look for the fine print there. I'll mention these really briefly. Binocular viewers, there are these doodads, right? So essentially, it splits the light path from the telescope into these two eyepieces. So it kind of looks like binoculars, but it's a little bit of a cheat. Some people really like these. I don't. It's a personal thing, okay? If you have this, obviously you have to buy two eyepieces, right? Because one for each eye. For some people, it's a lot more comfortable to view because you don't have to squint, and close one eye when you're looking through the telescope. But on the other hand, you have to adjust it a little bit more to get it just right. And you want to be clear that it doesn't really create a binocular experience. If you truly look through binoculars, you get a 3D image because the binoculars are really looking at the world from two places, like the ones that Carl has here, right? So those binoculars, each eye gets its own lens. Here, each eye really shares the same lens, right? It's just coming through the same telescope. So it's not the same as binoculars. But again, some people really like these. It's a personal thing, no problem. Reminder on magnification. Recall that more magnification is not always better, right? Some targets are really large and need low magnification. As magnification increases, eye relief goes down, right? Might be a problem for glasses. Your image will get dimmer. Atmospheric disturbances become more noticeable. And mount instability may be a problem, right? Actually, if you magnify too much, sometimes the whole image shakes quite a bit because the mount jiggles. Even just a little breeze might jiggle your telescope, right? So the lesson here is don't go nuts buying eyepieces for high magnification because you may never use them, right? A lot of people have that kind of experience. And let's see, really quickly here, we're almost done with this. Astronomy may require some bodily contortions, right? Like we said earlier, imagine you're trying to look straight up at the zenith, right? Your object is right there, and the light is just going straight through. What am I going to do, right? I'm going to be like, somehow down here if I don't do anything special, right? So, yeah, if I have to just put my head right here, I'd be looking straight up if the scope is pointing straight up. We can't do that. Instead, we do this, right? We put a little mirror here. It's called a star diagonal. So I actually look into the eyepiece here. Okay, and that way, if the scope points straight up, I can look, basically straight ahead. Does that make sense? Right. So yeah. So we put this to make ourselves less of a gymnast here, right? And so there's a star diagonal, yeah. Basically, we just talked about this. So these things also come in various price ranges. If you buy a telescope kit, sometimes a diagonal is a pretty cheap thing. Probably good enough to get started. Later, you may want to buy a better one, higher quality mirror inside. So they also come in different price points. Yeah, here's just some more examples, right? They can differ in terms of the mirror material, the coating, how flat is the mirror, how perfectly is it shaped, in general build quality of these things. You can kind of see, already this thing just looks cheaper than this, and it is, and this is $50. This is a $200 diagonal. Quick note on, earlier we said that, this is the normal view of the Golden Gate Bridge. If you look through the telescope, it flips everything around, right? Now, if you add a star diagonal, the diagonal actually unflips the up and down. So now up and down is correct again, but left and right are reversed. So, so again, just want to be aware, depending on what you're looking at, right? How your telescope is either flipping or unflipping things. Because if you're trying to compare what you're seeing through the scope, maybe to a star map, right? Things could be flipped. Does that make sense? Right? Your star map will be drawn the way it just looks in the sky, naked eye. But if I look through the telescope, like this, notice that the stars you'll see will actually be flipped. They'll be correct this way with a diagonal, but they'll be flipped this way. Without a diagonal, they're flipped all over, right? They're flipped in both directions. So just have to know to expect that. Quick word on focusers, right? So like we said earlier, there's a mechanism to pull the tube apart or together, right, to adjust focus. And again, if you buy a cheap scope, it may have a really cheap, crappy focuser, right? It could be very difficult to get good focus. It may be shaky, jiggly. It may not hold position very well, right? On the other hand, we've got these super fancy focusers that cost hundreds of dollars. And again, they're really nice. But all you really need is a decent focuser, right? And so, for example, this scope is not fancy, but it's decent. But be aware, you'll see this. Sometimes you pay extra money for focusers. Okay, and with that, we'll take a cookie break, stretch your legs, and then we'll talk about mounts, and then we'll wrap up. All right, so the mount, right, is a critical component because the telescope sits on it. So there are alt-azimuth mounts, equatorial mounts, and then we'll talk about some properties of these mounts. Okay. So the mount has to hold the whole thing up, right? It has to allow the telescope to be pointed, and importantly, it has to hold the telescope firmly and provide for smooth motion and be stable, right? And you'd be surprised, something can look stable, just looking at it standing here, but when you look through, it can be jiggly like Jello, right? So, yeah. So, like we said before, you have the mount head, like, whoops, sorry, wrong button, like this part here, right? And then the tripod, or sometimes you have this thing called a pier. That's more for more permanent installations, the piers. And then there's some way to, of course, attach the telescope to the tripod, right? So there's a little doohickey there, and that's where they mate. And that attachment is sometimes brand specific, sometimes not. So sometimes you can reuse a mount for something else, sometimes not. So stable mounts tend to be heavy mounts. This is often the catch, right? You're trying to take a mount to the field. You got to be strong for this. Start pumping iron now so that you can carry the mount that you want to buy in a month. Okay, and the larger your scope gets, right, the heavier, more sturdy the mount has to be. Okay. So like we said, for some scopes, the mount is permanently paired with the scope, and cannot be used for another scope, right? So you're just kind of stuck with those two things, just mated, and that's it. But many mounts can be used for different types of scopes, and then there are two ways to attach. And they're like these two rails, basically. This is called a Vixen rail. This is called a Losmandy rail. These are just company names. They became de facto standards. So like Kleenex, we now just say Vixen rail, right? These tend to be used for the smaller scopes. These tend to be used for the larger scopes, the Losmandis, right? So Vixen smaller, Losmandy larger, and then some mounts actually work for both. And this is important because you don't want to buy the wrong mount for your scope, of course, right? So if you end up buying these separately, make sure they fit together. And every mount has some maximum carrying capacity. Exceeding that capacity will result in poor stability, or worse, you could actually destroy your mount, right? If you put too heavy of a scope on a particular mount, right? You might damage the gears or the drive mechanism or something, okay? And so when you're choosing capacity, consider the weight of all the accessories, not just the optical tube, right? Because this all adds up. So here we have the optical tube, but then there's a finder on it, the eyepiece is there, right? The diagonal is there, all these things nickel and dime together. And before you know it, hey, you might have added another 5 pounds or whatever, okay, and need to consider that. And you really don't want to load a scope or a mount to its maximum. I mean, yeah, it'll work, but it probably won't work well. It'll be jiggly and shaky. So, some rule of thumb is maybe, leave 20% margin for visual use. For photography, you want to leave even more margin because the camera will pick up jiggles more easily than your eye effectively. Okay. Right, then we have these two types of mounts, alt-azimuth mounts and equatorial mounts. And there's like different flavors, things called German equatorial mounts, center balanced. A new thing that came over recent years is strain wave or harmonic mounts, and there are things called wedges. These we'll talk a little more in the add-on video. And some mounts are actually convertible between these two flavors, and we'll talk about each of these flavors a little bit in a second. And then mounts can also be manual. We just talked about the Dob, right? Some of us, you just manually swivel it around, right? There's no motor at all. You're the motor. Okay. And then other mounts are automatic, or we call them go-to mounts also, right? Because you can tell the computer to go to some object. Okay. And there are some semi-automatic things where sometimes on a Dob, there's a computer that tells you where to push it, but you have to move it. Right? So it's kind of an in-between thing. You get help finding something, but you actually have to do the work of finding it. And then if you do have something that has automation, there is some alignment step required, right? So you may still have to do something to prepare it for the night. So while we're observing a celestial object, right, the Earth is rotating all the time. It's really inconvenient, okay? Because things keep moving in the sky. If they would only hold still, it would be so much simpler. But yeah, the Earth is rotating at 15 degrees per hour. Okay, so that means objects, appear to move in the sky, and they'll move out of the telescope's field quite quickly. Right? We were just saying this, right? If you look at the moon, right, it's going to be cruising, right? Way more than you would expect. So yeah, within 2 minutes, the moon will have, moved its entire width, basically. So if it's a manual mount, you have to chase the object by hand, or if it's a computer mount, the computer has to do the chasing for you and keep the scope moving. Learning to track objects may take some practice, but it can actually be a fun thing to be doing, right? And like we said, automatic mounts, once aligned, can actually do that work for you, which comes in handy under some conditions. So the alt-az mount, has two perpendicular axes for rotating and positioning. Basically, altitude is this one, right? That's this axis. And azimuth is this one, right, along the horizontal. And if you're trying to track something, you have to move, in both axes, right? You're moving the up and down and the right and left, together. And so these are all alt-az examples, right? The Dob is an alt-az. This guy, same idea. There's a swivel axis here and a swivel axis here. It's the same thing, right? You move it this way or you move it that way. These are all alt-az ones as well. Single fork, double fork. These are more stable than this one, right? But they're all alt-az designs. Computerized alt-az mounts, they require some initialization step, like we said, right? You have to tell it, first of all, what's the current date and time, right? Because it needs to know. Because on a different day, right, the sky will look different, right? So it needs to know what is today, right? What's the time? And it also needs to know where it is in the world, because if you're looking at the sky here versus Australia, the sky looks different, right? So you need to know location and time. And then it also needs a couple of reference stars, right? So the first two here, I kind of tell it, okay, I'm in Hoagie Park and it's Sunday, right? But then, which way am I facing? It doesn't know yet, right? So for that, you have to tell it, oh, there's one reference star, and there's some other one, and then it knows basically which way it's facing. Does that make sense? Right? So effectively, you always need those kinds of initialization steps, right? The time and place may come from a GPS device. That's very convenient. These are automatic. And then the alignment to a reference star may be manual, and often is, but sometimes there's also automation for that if you want to spend more money. Right? Alt-az mounts have an effect called field rotation. So let's think about that for a second, right? So let's say we're looking at Jupiter. It's just rising over here, okay? And so, as I see it come up, I'm looking this way, and I see Jupiter looking like this. And I'm pointing my telescope at it, okay? Now, as Jupiter goes across the sky, right, Jupiter's going to do this, right? So whatever appeared at the top here, by the time it goes over here, will be kind of on the bottom. Does that make sense? That's Jupiter's path. But if I have an alt-az telescope, the telescope does this, right? So the top of the telescope is the same either way. So that means if I'm looking at Jupiter the entire time, Jupiter appears to be flipping over as the scope is tracking this way, and Jupiter is actually doing this. Does that make sense? Yeah, and so this is kind of what I'm trying to show here, right? You look at the beginning of the night, in the middle, and at the end, right? And Jupiter is actually tipping over. Not a big deal for visual at all. For photography, within 30 seconds or so, this matters, right? So that's why alt-az mounts may not be great for photography unless you can keep your exposures to like 30 seconds or less. Okay. Equatorial mounts solve this field rotation problem by creating a different kind of complexity, right? So equatorial mounts have one of their two axes positioned so that the axis aligns with the Earth's axis of rotation, right? So, so here's the Earth spinning, right, and it's spinning on its axis. Excuse me. And the idea is that, the equatorial mount, you have to set it up such that one of its axes is always exactly parallel to the Earth's axis, right? So that kind of looks like this, right? So here, again, here's the Earth's spin axis. And then the telescope has this thing called the RA axis, and that axis lines up with the Earth's rotation axis. So how do you get there is a good question, but that's part of the alignment step, right? You have to jiggle the telescope so that these axes align. And so the RA or right ascension axis, once you have that aligned the way it's supposed to be, right, then that's the only thing that needs to move for tracking, okay? Because as the Earth is turning, you just move along the RA axis the exact same way, right? Because these axes are essentially on top of each other. The other axis is the deck axis that allows the scope to swivel in the other dimension. And you only need to move that one to locate a new object. Once you have it, you leave that one fixed, right? And just the RA axis moves, and that effectively solves the field rotation problem. But you need this, what we call polar alignment, right? You have to get the RA axis pointing just right. And here's just another picture of this, right? So Earth's axis, on the RA axis has to be, correct with regard or aligned to the Earth's axis. This can be tricky, right? If you're doing this for the first time, we're happy to help you. Okay, this is not meant to be a tutorial now on equatorial mounts. That could be another separate half hour, easy, right? But just be aware there is this step to learn, okay? And there are tools that can help you with this. In the northern hemisphere, right, it's actually not so bad because we have a star that's really convenient for this, right? Polaris is the North Star. It's almost perfectly sitting under our axis, right? So I always think of it like, imagine you put a big chopstick through the Earth, right? And that chopstick is the Earth's axis. That chopstick is pointing almost perfectly at Polaris, purely by luck, right? But it's very convenient because we can use Polaris to help align our equatorial mounts. And there's some other alternatives if you cannot see Polaris, but this is typically what we do. In the southern hemisphere, you're out of luck. There's no Polaris there. So the folks who live in Australia, they have a much harder time doing their equatorial mount astronomy. You guys should all consider yourselves lucky, for being here. So precise pole alignment can be tricky even here, right? For visual eyepiece use, not that big of a deal. For astrophotography, you really want it to be perfect, right? So you get perfect tracking. Take some practice to get this right, and there is technology to assist if you want to spend money on that. These are different examples of these kinds of mounts. You can just see they get, this one looks kind of dinky, and it is pretty jiggly and shaky. This thing is massive and also quite expensive, right? So, again, there's a spectrum here, right? Depending on how much money, what you're trying to achieve. And remember that when you go to photography, right, often people throw a lot of money at the mount because that's a key component to take long exposures, good long exposures. So like we said, mounts can be manual or motorized. Manual mounts can be alt-az or equatorial, right? So they can be a lot of fun to operate, right? So we talk about some of the automation, right? But don't discount just manual devices, right? You learn a lot more with it, and it's also cheaper. And there's a technique called star hopping, right, to locate objects. So this is also something you could learn if you come out, hang out with us, at star parties. But you have to constantly, keep in mind, you have to constantly adjust your mount to track. The automatic mounts, right, they do a lot of that tracking, locating and tracking for you, but you have to set them up before the night really starts. And So like we said, you need location on Earth, like GPS. You need time and place. You need some reference stars, right? And then each mount has its own procedure for this. They're similar, but they're not identical. All have the same objective, but one, the other one could be a little different. You'll be fine if you switch, but just be aware, right? There are differences. And like we said, some offer alignment features that make it less or more easy. But it is good to learn how to do these alignments manually, right? So that you're not stuck always relying on the technology. So different mounts do offer, let's see, hold on a second. So different mounts offer varying targeting and go-to accuracy for finding objects and tracking accuracy. For example, so we have the Celestron C8, the orange tube, right? There's one over there and there's one over there. Same tube, exact same optical tube, but the mount is different. And we saw earlier that that mount is a little less expensive than that one. So the extra money you pay for that, it does buy you something, right? The mount mechanism has a little more carrying capacity. It has better tracking, go-to and tracking accuracy, right? So you're going to do an easier job finding an object with that thing than with that one, right? So again, trade-offs, right? And so those differences come from the internal mechanisms, like how good are the motors and the gears, and the software that's in the mount. And be aware, if you have these automatic mounts, everything has software, right? You may be doing software updates at some point, right, to address some problem, right? It's part of the game these days. So we mentioned centering eyepieces briefly earlier. And so this is where they come into play, right? If you're trying to align the two stars, we said you need time, place, right? And a couple of reference stars. And so when you're trying to align a telescope mount to the reference stars, you want to try to center that star as accurately as possible, right? It should be ideally perfectly in the center of your eyepiece. But what's the center? I don't know, right? Well, that's where this helps, right? So these eyepieces have, like a little crosshair inside that you can light up so you can see it in the dark, and that allows you to center more accurately. So it's not required, but comes in handy, right? It's like an optional accessory, but it can help you improve your alignment accuracy, which will then give you better go-to and tracking accuracy. Does that make sense? Yeah, okay. Oops, sorry. This is the part we're going to skip. We'll cover in the video, so I will go and do the skipping. Actually, I think I already mentioned this coincidentally, right? So between these two guys that you can actually see on the floor, I know here the mount, the telescope tube is gray, but it's the exact same thing, right? It's just different paint. Here essentially we have a higher quality gear mechanism and motor mechanism, right? So this will just behave more predictably, track better, go to better. But if this is in the budget, it's okay. You can get this to work. It's fine. I had one of these, and actually I still have it, right, and still use it, just like what Carl has there, right? So it's all trade-offs. For a Dob, you don't really have motors or gears, although there are actually fancy Dobs that have drives for tracking, but that's pretty rare. But even, and often people buy these like secondhand, actually. You can get pretty good secondhand deals on Dobs often. But you want to make sure that, the mechanism is good. It has to be nice and smooth. You don't want it to be sticky, right, when you're manually pivoting the thing around. Because if it's sticky, you're going to have a really hard time making fine adjustments. And so, you definitely want to try this out if you're buying a used Dob. Is it easy to move it just a little bit, right? Because that's what you're going to be doing when you're trying to track an object. Does that make sense, right? So even on a really simple manual Dob, you still got to think about the tracking mechanism in a way, right? Because it has to be nice and smooth. The final thing here on balance, right? So regardless of the mount type, telescope usually needs to be balanced on the mount, right? So, and you didn't see me do this, but before you guys came, like for example, I was moving this back and forth so that right now there's a clutch holding it, but if I release the clutch, we fiddle with it some, so it's a little, but notice it just kind of hangs here, right? It's not obviously swinging this way or swinging the other way. Does that make sense? Right? So this is often a step that people who are doing this for the first time kind of miss, right? It's not always explained well enough in the manuals or whatever, right? So balance helps, or sometimes it's absolutely required, okay? And some equatorial mounts require heavy counterweights for balance, right? So again, more weight, more stuff to carry around. All AS mounts sometimes also need counterweights for things to work, but mostly counterweights are needed here. There's a cool new thing called the strain wave mount. Discuss this more in the video content if you want to follow up on that. Actually, and there they are, but I just said we're not going to do them, so I need to hit this button. Hello. There it goes. So just quick trade-off again. Alt-as mounts, they're really simple to set up, right? It's very few parts generally. Intuitive pointing model, like Carl was saying, right? Up, down, sideways, straightforward. we all know how to think that way. But you have this field rotation problem, right? That can mess you up if you're trying to take pictures. For visual, no big deal. You don't have to worry about counterweights much here, but sometimes you do. And often these guys are lighter overall, but they may come in fewer pieces. So each assembly may be reasonably heavy. Does that make sense, right? So you may be stuck with certain things that are permanently bolted together. So the whole solution may be less massive than the alternative. But each piece may be a little more awkward and heavier sometimes. Like one of those fork mounts things we saw, like the double fork, they're permanently attached, right? So you don't separate them. You just have to carry the whole thing. On the equatorial, right, the alignment can be tricky. You have to learn this polar thing. The RA deck coordinate system, like Carl was saying, right, can be a brain teaser. And I have the same problem. It's like, wait, this way? No, that was wrong. And you're like, okay, right? You have to get used to how that's turning. It's not intuitive at first at all. But you don't have this field rotation problem. You may need counterweights. And the mount overall may be much heavier, but it typically comes apart into more pieces. So each piece may be easy to transport, but the whole thing could be quite massive. Make sense? Yeah. So again, trade-offs, right? How much do you want to carry? What can you easily store? How much trouble is it to set this up quickly? And actually, I think I already mentioned this, right? So if you're buying a used mount, right, can be attractive and sometimes a great option. But regardless of the mount type, make sure you test the full range of motion, right? Like if it's an automatic thing, run the gears, spin the thing all the way around, all the way through. Make sure no place does it go, right, or stick or do something funny, because sometimes that happens, right? The gear may be damaged in one point, and you have to go all the way around to notice. Does that make sense? Right, so, yeah. GPS mounts, software has bugs, hardware has bugs. So we run into this sometimes. People come with older mounts, and they're trying to use their GPS, but there've been various software issues or design issues around GPS. It's like the Y2K bug. For those of you who remember, it's sort of a variant of this, right? There was a 2019 GPS rollover bug. If your mount is that old or older, right, you may need a fix. And that may be why your mount's not working. This happens to us, right? People bring in their stuff, and it's like, why is it not working? It's because of this, right? Yeah. So these are just things to think about if you're buying, secondhand equipment. You may have to do some investigation and repair. Okay. Finder, I think I'm doing this one, and then we're doing binoculars, I think, right? So just quickly on the finder, we said this is also super important because otherwise you may not find the thing you're trying to look at, right? The moon's right there. Pointing to it can be really hard, even though it's like right there. Okay. Because the scope is only showing you 1 degree of sky or less, right? And then you might be tempted to just sweep the scope around to try to find your moon or whatever, but that almost never works well. You just keep doing this, and it's like I don't know where I am. And so the idea is that we need some tool to do this, and they're non-magnifying and magnifying finders. These are non-magnifying finders. You can see them here on the scopes. They basically project, again, it's hard to see on the projector, I'm sorry, but they basically project like a bullseye ring pattern onto the sky. And so if you look through that and you place your star or whatever in the center, it'll be in the telescope. Okay. And they come in a couple different, variations here. And then there are magnifying finders, where you basically have like a mini telescope on here, right? It's like a little telescope attached to the big telescope, but it has a much wider field of view, right? So you can see much more of the sky. And therefore, it's much easier to find the thing that you're looking for, right, and get it centered. And then you can start looking through the big telescope, right? And they come in different apertures and magnifications. Yeah. Okay. These are just some different examples of this. Some of them are straight through. Some have diagonals, and some have, again, crosshairs with lights inside. And yeah, so you have this trade-off, right? Non-magnifying finders are useful for finding bright objects, aligning automatic mounts, and for star hopping, right? If you're trying to learn how to locate objects just by using some reference star, like I know I need to find this star, then I need to hop 2 degrees over here. That's where my galaxy should be or something, right? So for that, these non-magnifying finders that project the bullseye are great. Magnifying finders are useful for locating fainter objects that are not close to bright stars. It's really hard to star hop there, so you know it's vaguely over here, but you want to look through, some magnification, right? Through that little finder scope, right, to be able to find it. All finders have to be aligned. We talked about that briefly earlier a little bit, right? This is often a step that new telescope owners trip over, but be aware, yeah, so you have to make sure that your telescope doesn't point this way and your finder points that way, right? That doesn't work. They have to be obviously looking at the same thing. So that requires an alignment step. That can be tricky the first time you do it. We're happy to help if you need. And then here, okay, we're not doing these. These will be extra video content. Okay, smart telescopes. Mr. Carl.
Okay. So let's talk about some things that are, I don't need this guy anymore. Let's talk about some things that are alternatives or complementary to telescopes. So we'll start with smart telescopes. And what is a smart telescope? These are all examples of smart telescopes. You can see their prices range from $300 to $4,000. So again, wide price range, even in this category. This is a Vaonis, a Seastar, Celestron, Dwarf Labs, Unistellar. These are some of the brands that produce smart telescopes. And what these things are at their core is they're a neat little package. You can kind of see some of these have interesting shapes. The Celestron one looks like an SCT that we have around the room. These other ones, this kind of looks like a refractor. These other ones look like a robot or something out of science fiction, right? They look totally different. They're all different types of refractors or reflectors that we've discussed before, but they come in this neat package that's sort of an all-in-one thing. And so something like the Seastar or this Vaonis, you can set it down on the ground or on a table. Maybe you level it, but that's about it. And then with an app on your phone, you tell it to start an alignment process and it will automatically align itself. And then you can, again, through an app on your phone, select targets. It will go to those targets and it'll start imaging them. And then you'll see the picture come up on your phone. And so all that together makes it a smart telescope. You have to do very little alignment, very little setup. You don't have to do any of the finding, and you don't have to even move to see the image. You just look at it on your phone. So these can be really attractive, right? We just spent almost 3 hours talking about how you need to do this and that with eyepieces and all this stuff, but now just plop it down and look, you see pictures, and you will see, again, these are pictures showing up usually on your phone. They're digital images, so that's not, the photons from M51 26 million years ago hitting your eye directly. They're hitting a sensor and then you're seeing them. But of course the advantage is that you can collect a lot more light. You can take many exposures and then stack them together, and that gives you a brighter image, a more colorful image. And so these are results that you can expect to get pretty close to this even here in San Jose with enough exposure time on a smart telescope. So no eyepieces. There is actually, I think, a Unistellar or a Vaonis has one that has an electronic eyepiece. It's a really expensive Nikon-produced thing, and I don't know why, but it has it. And yeah, we discussed you see them through your phone or tablet. And so in comparison, this is astrophotography, essentially. These are examples of more traditional astrophotography rigs, and you can see a refractor. You can see this thing on the end is actually a camera on the left-hand side, and then you've got a whole bunch of other electronics. You've got a finder. You've actually got another camera that helps you guide and correct for tracking errors. You've got this little computer here that's essentially controlling the whole shebang, and the whole rat's nest of wires, and then a little power box under there. So, compared to this, the smart telescope is a really compact, easy thing to use. However, it does have its limitations. You notice from their size, most of them are fairly small. The Seastar main model is a 50 millimeter lens. Celestron has a version, the more expensive one, that goes up to a 6-inch kind of reflecting style telescope. And so your results will vary. And they're also on alt-az mounts. So like Wolf mentioned earlier, because of that field rotation effect, you're limited to how long of an exposure you can take without things starting to trail and get blurry. And so these on equatorial mounts with dedicated cameras and more expensive optics can produce perhaps better images overall, but it takes a lot more work. And so related, if you were going to go down this astrophotography route, you would use a camera that looks maybe something like this, kind of a cylinder. This middle one is a cooled camera, so it's like deeper, it's got a fan, and it actually has an electronic Peltier-style tech cooler, which is kind of an interesting technology that you apply electricity and one side gets hot, one side gets cold, and the cooling is nice because the sensors that we use, or that are used in these, are really, really sensitive. We want them to be sensitive because we're looking at dark things. But because they're so sensitive, they're more susceptible to noise, like from the actual electrons moving around in the circuitry. And that noise is reduced when the temperature goes down, it turns out. So cooling is a desirable effect in a camera. This camera on the left is not cooled, so it's shorter. Another interesting thing about this camera in the middle is there are actually two sensors. So I actually just got a camera like this, a 2600 MC Duo from ZWO. And the main sensor is where you get your big, beautiful galaxy image. The secondary sensor is one that is used for something called guiding, which is something that allows you to track a smaller portion of the sky and just a few stars. And if you did that polar alignment and it wasn't exactly perfect, I mean, let's be real, it's never going to be exactly perfect. Things will kind of drift from time to time. But actually this secondary little sensor built right into the same package can be used with software to detect that motion and kind of nudge it back on track so that effectively cancels it out. This also is more of a deep sky camera because it has a larger sensor, it's cooled. This is typically a planetary camera. The differences between these two, so like here you want really high resolution, just like any camera that you're taking pictures with in the sky. Here the resolution doesn't matter as much because the planets are really small, but you're going to zoom in so far. What matters more for planetary is how many images you can take in a short amount of time as possible. So here we mentioned that image stacking. You're going to take tons and tons of images, and so these actually tend to be used in video mode. And so these are optimized for a really small, typically a small resolution, but really fast frame rates. You can get all those images. Anyways, this is not an astrophotography talk, but and then finally over here we have a computer that controls everything. Yeah, do you want to?
No, I was going to say, astrophotography could be another hour or two, right? Like we said, there's so much to discuss with cameras and all that. Like we said, we spent 2 days, right? On all this stuff. You never probably would do it.
Yeah, we'll never finish. So I'll move it along. So smart telescope caveats, right? Like any telescope, there's no best one. There are a lot of different trade-offs. Cost, so $500 will get you a C-star. 4,000 might get you that Celestron 6-inch one. Aperture, right? The smallest is 30 millimeters, and then there's the 6-inch one, which would be 6 times 25 something. 150. Thank you. Yeah, you got to update that new model. Image acquisition time, many minutes. Image resolution will vary. The smart telescopes typically have a smaller sensor. Field of view, tracking, accuracy, et cetera, et cetera. Lots of trade-offs, just like all the other ones. And also, you're reliant on sometimes a built-in battery. Sometimes you can have an external power source. But if that built-in battery fails, then it's kind of a closed system. Maybe you can't replace it as easily. And if the software doesn't get supported well, then nothing works. And they don't replace visual telescopes. They're typically complementary.
And you can't upgrade those lenses or anything.
You can't. Yeah, I mean, you could if you wanted to get really fun. I mean, you're not going to change the lens on your refractor either. You would buy a different refractor. But yeah, there's less that you can tinker with. So let's talk about binoculars. Binoculars are.
Hang on,
yeah.
you want to take the other link here to go to your content? Go back up one.
Oh, okay.
Yep. Sorry.
Ooh, special link.
Yeah. There you go.
Aha.
These are the ones you want.
Okay, great. These are my slides now. Binoculars. An alternative to telescopes. I've shown a few of these funny-looking binoculars, and then you're probably more familiar with traditional binoculars like these ones here. It's a great alternative to telescopes. You can see typically wider field of views. And of course, depending on what you're using them for, the ergonomics are different. So it's portable. It can be more comfortable looking through two eyes than one. The two-eye viewing also has advantages. Your brain is pretty used to using two eyes. If you are lucky to have sight in both of your eyes, you've been using that your whole life. And so that has advantages when viewing even dark things. Better contrast, better, it looks better. And then binocular apertures tend to vary. I think the largest aperture I've seen in binoculars is maybe 110 millimeters, 120. But that's a big binocular. So they're typically between 50 and 100. And their power tends to be lower, typically between 7 and 20x. And then depending on these funny binoculars where you can switch out eyepieces, you can manipulate that up to maybe 50x or more. But again, as we discussed earlier, a huge magnification without a huge aperture doesn't really help you that much. But you get a huge field of views, right? Maximum around maybe 6 degrees compared to a degree or less from a typical telescope setup. And then if you're using the traditional binoculars, they have prisms that right side up the image. So you could look at things on the ground and see them as expected, like birds or whatever. So good targets for binoculars. We talked a lot about the Pleiades earlier. They're 2 degrees roughly in extent. Andromeda is a similar size, 2 degrees in this like main disk area. And so those fit, max 6 degrees, typical binoculars between like 3 and 4 degrees. So those fit really nicely into binoculars. So you're looking at really bright deep sky objects like Andromeda. You're not looking at really faint things like planetary nebulae. You're looking at comets, perhaps. Comets that have a really long tail. So some of the great comets that we've had in the last couple years have looked really nice through binoculars. Star clusters, anything big is great for binoculars. And then we've talked about this to a great extent, right? I'm showing images that I took with one of my really complicated astrophotography rigs. But if you're looking at them, they'd be much dimmer, not colorful, etc. So there's a few things to consider when we're talking about binoculars. So I'll just quickly go through some of these. First thing is you're looking with 2 eyes, right? And so because you have 2 eyes, they are separated by some distance. And that distance is actually slightly different, potentially, for everyone in this room and everyone everywhere. It tends to fall within a range of like mid-50s to mid-60s. And the average is different for males versus females. But this is a consideration that you need to consider when looking at binoculars. What is the IPD range? What is your IPD range, which you can measure with an app called PD+, I think is free. And you get a number, like mine is 64 millimeters. And the binoculars will have a spec that says what IPD ranges it supports. It'll have a range, a minimum and a maximum. And you want to make sure that your IPD is well within that range so that you can use the binoculars and you can get the eyepieces in the correct orientation so everything will look good. Speaking of which, we talked about collimation earlier, right? Aligning optics. Binoculars also need to be collimated, but they have this extra dimension of collimation, right? Because you're looking through each eye. So not only does a single eye's worth of binocular, like that telescope portion, that needs to be kind of aligned correctly. But ultimately the view that comes out of those has to be aligned with each eye. So like if one optical component, or your right eye, is looking at an object and it's up here, and your left eye is looking at an object and it's down here, well then when you look at it, you're going to see double, right? You're going to see kind of like this is left and right. You're going to see like, oh yeah, it's sort of over here. Same thing if you if you put your hand really close to your face and you try to look past it, I see way more fingers than I should. And it's the same sort of effect. It turns out your eyes are really good because they're already separated in this way. Your brain is actually really good at merging images if they're a little bit offset, like left and right. So you can get away with that a little bit. But if they're up and down offset, forget about it. You're going to see double. So that's something you need to consider with binoculars. Make sure that you can merge the images correctly. And then kind of the last thing, these two things are related. The viewing angle matters, right? We talked a lot about this with the star diagonals, and like if you're using these traditional handheld binoculars, they're straight through, and you want to look up, then you're craning your neck, and that's not going to last very long. Likewise, if they're heavy, you may need to mount them. And so here are a couple different ways you could mount binoculars. This one is my favorite because you get to lie down in a lounge chair, and you've got this this mount, which is actually called a parallelogram mount, and it has a series of counterweights and such that the binoculars will sort of stay put wherever you sort of move it into position, and then you can also move them up and down. So without changing what you're looking at, which is really handy. So you could show the view to someone who is much shorter or much taller than you, or you could, grab a chair and kick back and look at the sky. And then there are other binoculars like the ones, my homemade ones, and some other commercial models that give you sort of a star diagonal experience. They put the image at a right angle or maybe a 70-degree angle from where it's coming from, so that you can look up without having to crane your neck and mostly look straight. Because most of the things we're looking at with nighttime binoculars, everything is above the horizon. So, the comfortable viewing angle should be more up here rather than straight ahead. So binoculars, there are two types of typical binocular designs that you buy commercially. They each use prisms. One is called a Poro prism design, and they always look like this. You can see they're kind of wider on the outside than they are on the inside. And the other is a roof or pentaprism design, where they're kind of this rectangular shape. There's no part that's wider than any other part. And these are interesting in their own right, but they're essentially refractors. Right? They have a lens here, and these prisms serve a couple different functions. One is just to redirect the light, so you can kind of see how this particular prism bends at these two angles and those two angles, and it comes out. And by the way, you have an eyepiece here as well, just like you have on your telescopes. It's just in the commercial binoculars, they tend to be built in, so you don't get to switch it out. You're stuck with whatever you get. And then in the roof prism, light takes this even more convoluted path, but pretty much goes straight through. So yeah, it's similar to everything we discussed. Lens, objective lens, ocular lens, some stuff in between to move the light around. And that's good. The other thing the prisms do is they do some work in terms of flipping the image. So each path through these prisms produces some amount of flipping one direction or another, and they're configured such that even though the lens is giving you that upside down and flipped image, when it comes out the eyepiece, you're getting something that's right side up and not flipped. So I have a few examples I'll try to run through fairly briefly. So here's a solid pair of binoculars, Celestron 10x50s. One thing we should note, this nomenclature, 10x50, has a little bit cryptic, but once you know how to decode it, it's super simple. The first number is the magnification, so 10x. You can kind of tell, right? The x is maybe used for the 10. 10x magnification, and then the 50 is the aperture of each lens in millimeters. So each one of these lenses is 50 millimeters, and combined with the built-in eyepiece, it gives you a magnification of 10x. So these are great. They give a field of view of around 6 degrees, which is huge, nice wide field of view, good for seeing lots of cool star clusters that we like to view. They're handheld, they're relatively light, you can bring them with you wherever you go. They support a large IPD range, so 50 to 74 millimeters. That covers basically the max and min of any studied IPD values. They provide a certain exit pupil, right, because they have eyepieces like anything. These ones are only 5 millimeters, so like we discussed, eye relief, 18 millimeters, large eye relief. So like we discussed, that means if you're a glasses wearer, these might be a good fit for you. The exit pupil is 5 millimeters, so your pupil goes between 2 millimeters and 6 millimeters, depending on the conditions, and so that's pretty good. It illuminates most of your eye, and it's light. But the cons, you're basically holding this. Maybe you could mount it on a tripod, but then you're doing something weird. Maybe you could get a parallelogram mount, but again, you've got to build that. It can be awkward if you're just using it handheld, and also you're stuck with whatever eyepieces came with the thing. So, okay, you can buy these commercially available binoculars, which look a little more hefty. BT82, here 82 is the objective lens size for each lens, so 82 millimeters. You realize that you see there's no like X factor here. There's no other number because you can switch out the eyepieces, and we know that that magnification is relative to what eyepieces you're using. So that's going to vary. And then with this thing, it's bigger, it's heavier, so you've got to put it on a mount, and typically this mount head here is called a U mount. And so it holds them nice and securely. And you can see here also that angle. So these are designed for the night sky, right? Because they're at an angle where most everything we're looking at is above us, and it's more comfortable to look through in that sense. But then you also need a tripod that's going to hold this. So the tripod expense itself could run you an extra $300 to $1,000, and this particular model is $1,800 versus the 10 by 50s here in 2024 prices was $115, something that you could perhaps justify spending more easily than $1,800. So pros, it's stable because it's mounted. Cons, you have to pay for that tripod and the heaviness of it all. You can switch out the eyepieces. So this accepts 1 1/4 eyepieces. Remember, 1 1/4 and 2 inch are kind of the main classes of eyepieces we're talking about. These accept only 1 1/4 eyepieces, but that's a ton of eyepieces. So you can get better quality optics, better characteristics, magnification, field of view, all that stuff. And they're kind of pricey, so I'd call that a con. But the IPD is pretty good, 54 to 76 millimeters. So most people can use it. And eye relief will depend on your eyepieces. Okay, this third one is the funky one that I have sitting over here next to Larry. This is a home-built binoculars from a kit. It's a composite of 3D printed parts and a few metal parts for stability from the kit, a bunch of nuts and bolts, and it's mounted on like a video head mount that we would use for a camera for doing video, and a tripod. And so this is really cool. It's obviously not something you're going to hold in your hands. You're going to put it on a mount, so it is going to run you $300 to $500 for the mount head and the tripod, depending on it. This kit itself costs, with all the optics and all the material and whatever, costs between $650 and $900, depending on what optics you want to put in it. So that's a choice you get to make when you build this, so like the quality of optics that you use. You can see this sort of right angle shape. So there is a mirror in here. There's a diagonal, like the Newtonian secondary mirror, that just kind of pops the light over to a right angle. So again, we can look up easier. But otherwise, these are 80 millimeter lenses in these tubes that create the 2 light paths for each of your eye. And they have adjustability. You can move the IPD as you need to. These are kind of cool. There's a button on it you can play with later. There's a built-in laser finder, so you can press it. You could mount a traditional finder scope on top of this, like the finders we discussed, and or you could use the laser to kind of eyeball like where you are pointing towards in the sky to help you find stuff. And the cool thing about this, unique to this other one, this takes different eyepieces, costs $1,800. This takes different eyepieces, costs $650, but it also accepts 2-inch eyepieces. 2-inch eyepieces can give you a wider field of view at a lower cost and a larger exit pupil, so it is a more immersive experience. Plus, you get 2 of them, so looking through these with 2-inch eyepieces can be really, really, really fun, and you don't have to buy the $630 eyepieces, although if you did, I'm sure it would be even better. So you need to mount this on a medium-duty solution, and currently this is a DIY thing that you would have to build. And then lastly, binoculars can be big too. Binocular telescopes is on my list to build. These are 16-inch apertures each, reflectors, and obviously there's an office chair and a whole setup here to navigate it. But Analog Sky is actually doing an 8-inch binocular build this year that I'm looking forward to, and it should be more attainable than this thing.
There we go. All right, trying to wrap this up, right? So, we mentioned this earlier, so a reminder, additional gear to consider, right? You want a red flashlight. I'll show a little detail in the next slide. You probably need some power supply to, if you have any kind of driven scope, motorized scope. You may want some cases for your eyepieces. You want an observing chair. Maybe you want a roll-up table so you can set up things nicely, out in the field. You want some kind of sky map. You may need some dew prevention gear. I'll mention this in a moment. You may want some optical filter. You may want a collimation tool. This will be a little more in the video content, the add-on. And yeah, don't forget warm clothes and hand foot warmers. Maybe you need counterweights for your telescope and mount solution, right? Typical upgrades that you may end up buying later, I wouldn't worry about it too much immediately, but you may want to get a better finder, maybe a magnifying finder. You may want that illuminated reticle eyepiece we showed earlier, right, to help you align your automatic mount. And just otherwise, buy some additional eyepieces. Don't go crazy, right? This is easy. Everybody falls, well, I don't know about everybody, but many fall into this trap. It's like, ooh, cool, and you buy lots of eyepieces. In reality, people often end up using like 3 to 4, right? You don't need dozens. And you may want a better star diagonal. All these things you can kind of defer until you know better what you're doing, but these things you pretty much want to think about early on. So here are just these examples, warm stuff. Buy these hand warmers, right? REI or something. You pop it open and it generates heat. Otherwise, your hands will get cold and stiff. Even in the summer, don't discount this, right? It gets colder than you think it will. Table, observing chair, right? This is kind of optional. Chair you definitely want because you don't want to be standing or hovering all day. You may need some power solution. You may need a dew shield. So it gets damp outside pretty fast some nights, depending on the location. Water dampness will form on stuff, including your optics. And if that happens, you're done for the night. So we employ countermeasures, and one is this kind of a thing called a dew shield. We have one over there. We can show you more later if you want to ask about it. Centering eyepiece, we mentioned some kind of sky map, electronic or paper. Maybe you want some optical filters later, and you definitely need some kind of a red flashlight. Speaking of flashlights, they're really indispensable, right? Red light, not too bright, because you don't want to ruin your eye's dark adaptation. It's not just the pupil getting bigger. There's some chemical changes that happen in the back of your eye. All that can take 20 to 40 minutes. And exposure to white light, like even your phone screen, wipes it out in a second. Okay? And then you have to start from scratch. Right? So a lot of being able to see well, in the dark through telescopes is your eyes being properly adapted. And so you definitely want, some nice red flashlights to look around. Could be a headlamp, could be this kind of thing. Here's a really fancy one that actually has a white light and a laser in it. That's kind of cool. But key thing here is, definitely don't use white light or non-red light during observing. It will ruin your eyes, and you're just going to ruin your experience. And use a red lamp that really is a red lamp. Try to avoid using a white light with tape over it. It's not the same. It works in a pinch, but it's really not the same. Dew prevention, like we said. So Newtonian, is pretty safe. The mirror is all the way down here. This does not dew up that easily. So you're probably fine. You're not going to have moisture forming on the mirror here, most likely. However, for an SCT, there is this glass corrector plate right here. It dews up really fast. So we often put this kind of a dew shield, basically a hollow tube on it, right, that helps protect it. Sometimes these things are heated. If it gets dewy enough, cold enough, you actually add a heater to this. Refractors have their own retractable dew shields. You can see it on these guys. Again, sometimes you need heaters, actually, if it gets cold enough. Yeah, we just mentioned that. By the way, in California, we've got it easy. People who are really in places where it snows or gets really cold, man, they got to struggle with this way, way worse. But even here, don't underestimate this. Optical filters. Yes, I'm actually going to skip this here, right, in the interest of time. But you can catch the video to fill in that hole. So now you've learned a whole bunch about terms, trade-offs, right? Different kinds of optical tubes. Probably your brains are full, and you're probably wondering, what did we even talk about when we started? You may not even remember. I don't know, right? But so if you're trying to make some purchasing decision, think about what kind of targets do you want to look at, right? Are they planets, tiny targets, really big star clusters, right? May affect what kind of telescope you buy because of field of view, right? So those are things to think about. Of course, what's your budget? Size and weight, how many pieces does your telescope break into, right? Is it just like 2 giant pieces you have to carry around, or does it become 10 little pieces? What's the largest item? What's the heaviest item? So you know how to carry this. Where do you store it, right? Make sure you can store it in your home or garage. Don't store it in a place that's too exposed to the elements. It shouldn't get damp and cold and hot and damp and hot and all that, every day. What observing sites will you go to, right? That may affect what you buy, because some may be very damp, some may be not so damp, for example. How do you transport this? What fits in your car? How much work is it to set this up? A couple pieces, boom, you're done. Dobs, super simple, right? If you're setting up an equatorial mount, you're going to be fiddling around longer. You get a reward for it, depending on what you want to do, but in terms of all the tracking fanciness. But think about that. Do you like to tinker, right? Or you just want something, you push a button and it goes? And then, are you trying to plan for astrophotography? And, really look at, visit star parties and you can see what other people are doing that can teach you a lot about what you might want to buy, right? So our events are great for this, beyond looking at the examples here today, You can even, SJ even has a loaner program where you can borrow some things, if you're a club member and, try out some things before you buy. Be aware the telescope manuals often make lots of assumptions, right? Like they assume you know something you wouldn't necessarily know, so you might be reading and going, huh? Right? And so that can kind of ruin your experience. They may leave out important subtleties, and it may not be enough for a good user experience, right? So this is where you might need help. And common trouble spots includes aligning the finder, balancing the tube on the mount, completing a go-to mount's alignment procedure, dealing with sloppy mount mechanics, like for less expensive mounts. They may work well, but they may require some tricks to really get to work for you. It may be difficult to first translate star patterns from a map to the sky. So maybe everything's working, but you're looking at your map going, this thing should be there, and I don't see it, because it takes some practice to do that translation. And also just choosing the right eyepiece for the observing conditions at first can be tricky. I mean, we went through a lot of it, right? But still, it may take some practice. So don't worry if you run into this. You'll figure it out, or we're happy to help, right? Or your local astronomy club will be happy to help. Lots of resources on YouTube. Discussion forums. Cloudy Nights is a web forum. A lot of chit-chat there that's useful. Nothing beats, finding your local astronomy club, right? Like us. And consider making checklists, right, for the stuff you have to take and what your setup procedure is for your scope, right? There's no generic checklist, but you may want to make that for yourself. And don't give up. It's okay to feel lost and ask questions. We all did at some point, right? All of us, I had pitfalls, tripped over things. I'm sure Carl and Swami did, right? It's okay. We're trying to help you, maybe skip one of those, but you'll still trip over something probably. No worries. And with that, I'll say thanks. So you made it. Thank you for sitting, through this whole thing. I hope you got something out of it. You should go look at the stars and look for an email we'll send about the video, right? Because there is a bunch of additional detail that we skipped in the interest of time. And clearly, we need to move some more things to the video since we ran over, but I appreciate you giving us your time. And I hope you kind of got what you came for. You can have another cookie. Please give us some feedback and sign in if you haven't already. And we'll be around a little longer if you want to look at the equipment some more and ask some more questions. Okay? But thanks. You made it. We all made it. Okay, yeah.